Okay. So it's Okay, good morning, everybody. We started the third today after the introduction of the main mechanism of the formation of rock and geometry and kinematic of shear zone, for, information about foliation for fibrous growth. We started to go inside the mechanism of exhumation of the deep-seated rocks. So we will have an overview of the general mechanism, then an example from the Balkan belt in Western Europe. Then we will start to discuss about the Himalayas. Okay, so this lesson is divided in the point, general exhumation of orogens, the collapse of orogen, synconvergent exhumation, exhumation by transpression, and some example from the Estevariscan belt in Western Europe. Okay, exhumation can happen in different tectonic setting, in extension and post-collisional extension, during a synconvergent extension. Synon-orogenic extrusion is also a mechanism of exhumation of deep-seated rocks. The channel flow is another efficient way to exhume rocks. Also, transpressional setting is able to exhume rocks from the deep part of the lithosphere. And also, a last mechanism introduced a few years ago is a distributed ductile thinning. And I will show you an example at regional scale about the East Variscan shear zone, where you can see in the picture on the right just an outcrop of Paleozoic rocks in the island of Sardinia in the Mediterranean Sea. Okay, we can now distinguish in between uplift and exhumation. Because while erosion or denudation is fundamental in eventually exposing the deeper rocks at the Earth's surface, the mechanisms that drive the rocks from the depth to shallower crust are considered exhumation processes. And also denudation is considered as a process that removes part of the Earth's upper crust by physical processes that occur naturally. For example, glaciers, wind, water, landslides. Through this form of exhumation, sometimes heavily buried, rocks is uncovered and can be exposed. You can see on the right some picture from the book of Yardley and Warren 2021. So we uplift is moving it from the surface to the upper part. Exhumation means that the rocks lose pressure coming up. And in the last picture, in this one, you can see a mechanism of channel flow applied to the greater Himalayan sequence and the surrounding rocks in the Himalayas, where exhumation is by normal faulting to the top and thrusting to the south, helped by erosion in the front of the bed. It is also an efficient way to exhume deep-seated rocks or migmatites. Okay. What do we mean by exhumation by tectonic processes are any tectonic mechanism that brings rocks from deeper crustal levels to shallower crustal levels. These tectonic mechanisms occur in different tectonic settings, from extensional to contractional, collisional, and post-collisional. I remember that in the paper by James and Beaumont proposing the channel flow in 2001, they proposed that erosion is a very important mechanism to promote tectonic activity. From that point, people started to discuss if tectonic is the main mechanism or erosion is the main mechanism. Some people push uh, the thinking ahead and stated that erosion is a main mechanism and the tectonic is only a consequence of focalized the focused erosion. Actually, most people think that tectonics is a main driving mechanism and erosion help to exhume, to move rock to the surface. It is like these men working in this way. Uh, This is a tectonic mechanism, and erosion help to push um, materials from the earth. So it is more correct view. As my colleagues told us several years ago, if erosion is a main mechanism of exhumation in Scotland, we should have a very big mountain because a lot of raining. So just to joke. Okay, now we started to see the mechanism by trusting. Trusting by itself is not enough to exhume rocks because this is a piece of continental crust. You have here in red the thrust. You can move the hanging wall in the to the upper part. So this point moves upper and upper and upper. But if there is not erosion, the lithostatic pressure above this point, this rock remains the same. You move upper, but the pressure is the same, so not real exhumation. To exhume this kind of rocks, you need to erode the upper part of this large antiform, and in this way, the rocks are brought to the surface, and here the pressure is strongly reduced by removing of the upper material by erosion. Also, normal faulting or extension should be able to remove material from the upper part. So thrusting alone is not enough, but thrusting plus erosion or thrusting plus normal faulting in the upper part is able to exhume the rocks from the deeper part. This is a picture from the Caledonian Orogen in Scotland. Okay, you can have also the exhumation by tectonic extension. You can see the first model by extension of the lithosphere proposed by Mackenzie. It is a pure shear model. And in this model, you have a tectonic thinning of this part of the lithosphere. And this thinning goes decreasing pressure. So this mechanism has been applied a few years ago to the Greater Himalayan sequence. I will show you later. Another model of tectonic extension is a Wernicke asymmetric simple shear. You have a big main fault, master fault, cross-cutting of the lithosphere, and the thinned part is asymmetric with respect to the fault. The third one is the lamination model. Is a little bit different with the lamination between ductile lower crust, ductile upper mantle, and so on. But in this way, you are bringing a lower rock up to the surface. So also during extension, the footwall rock are exhumed during the deformation. A later model has been proposed during tectonic extension. There are hyperextended margins. So you have initial state of rift of the continental lithosphere. You can start to form conjugate extensional detachment fault with exhumation of these rocks. These rocks are moving to the upper part. You can see the green arrow. The kinematic brings the rocks upper. And the final exhumation, detachment cross-cut of the crust and expose the serpentinized mantle rock here. You can see this figure here. So in this way, you can exhume the lower continental crust and even the mantle only by extension. This mechanism has been applied also to the Alps. You can see reconstruction, a pre-orogenic reconstruction of the margins of the Alps. In the upper part, you can see a cross-section of the Alps made by Swiss geologists in Lausanne. You can see the Europe, the Adriatic African crust. You can see a strong deformation of the units in the upper part. There is a lot of detail in this part, mainly by geological mapping. There is a nice section by Emile Argand 1 century ago that proposed more or less the same geometry of this fold. just looking at the rocks and moving to in the field and mapping the rocks. Now, more or less the same figure has been confirmed by geophysics and geological studies. But if we give a look at reconstruction, so you have to retro-deform this complex situation, can have an idea of what happened during the Jurassic when the continental were rifted and there was the opening of ocean, Liguria, Piemonte Ocean. You can see the European margin, a small ocean, a small Moudinage continent, the Brianzone domain, the Liguria Piemonte Ocean, with the Adriatic distal margin, Adriatic proximal margin. This is Africa continent or Adria continent. And you can see that hyperextension brought continental crust above the mantle. You have outcrop in the Western Alps, also in the Central Alps, where you can still observe this contact between hyperextended continental crust above mantle rocks of serpentinite rocks. So this is more or less a, a very efficient way to exhume mantle and the lower and middle crustal rocks. Then, after convergence, there was a subduction of the oceanic lithosphere below the atrial margin. So this part went in subduction, and this part reached the high pressure and ultra high pressure metamorphic condition with coesite inside the garnets of the continental crust in the so-called Dora-Myra massive. So, okay, we will come back last day on this kind of tectonics, but just to see that it is possible to reconstruct also by orogenic belt the original situation. And this situation is particularly well exposed in the Central Alps, where the original contact are still well preserved. Okay, when we speak about exhumation by tectonic extension, we will speak about also core complexes. Core complexes are metamorphic core complexes where extension brought migmatite dome or depleted rock gneiss up to the surface. The shape is like a dome or a large antiform surrounded by mylonites. Uh, so you have a ductile deformation in this part of the core complex and the ductile brittle deformation at the boundary and brittle deformation in the upper part. This mechanism was usefully applied especially in the 90s. And by this way, people try to explain also the exhumation of high pressure and ultra high pressure rocks. So people thought that ecologites from a deeper part of the lithosphere could be exhumed by this kind of extension. The asymmetric extension is much more efficient to exhume rocks. But there is a problem because ultra high pressure rocks means 100 kilometers of dip in the lithosphere. So to exhume 100 kilometers, you have to extend several 100 kilometers of the crust, and it is not really possible. We can observe now extension like 1,000 kilometers or 2,000 kilometers. So you can exhume high temperature, low pressure rocks, but for high pressure or ultra pressure rocks, it is very difficult to explain only by this mechanism. You can sum up a different mechanism or use some other things. You can see also in this pressure and temperature diagram, you can see the different colors, the position of the rocks in the lithosphere. The blue point in this rock underwent shearing in the lower channel, this part. Then the green and the yellow contractional tectonics, because you are convergent to flow here. So little bit contraction in this part. Then, when the rocks are close to the surface of the upper part of the crust, they become to underwent extension by the movement of the myelonitic rocks in the co- in the rim of the metamorphic core. Okay, the first application of the mm, core complexes was on the continental crust in the western USA, the Western America. Mm, in Arizona, in Texas, there are very nice core complexes with beautiful malonites, brittle rocks above, but they are on the continental crust. After some year, people started to apply this concept also to the oceanic crust. So some oceanic detachment system and the oceanic core complex has been recognized all over the world. Also, in the formed oceanic lithosphere involved in orogenic deformation. The main difference is you can have the upper, brittle deformation by normal fault. Of course, if you have normal fault, you have movement of water towards the lower part, meteoric water. Then you have maybe geothermal system, uh, because here there is an increase in temperature and high heat flow. Uh, you have here the myelonite zone at the tail layer. In the continental crust is maybe at a few kilometers of depth. If you go in the oceanic crust, maybe the brittle data transition is 300, 400 degrees due to quartz rheology in the continental crust. If you look at the oceanic crust, you have to deal with olivine rheology, so the transition is at 600 degrees because it is a much more stronger mineral. And so this transition is shifted downward and downward, but the mechanism are really the same. So now people try to recognize this theory, the gabbro, that very common in the ophiolites, deformed in various orogens, such as the Apennines or the Alps. And sometimes this shearing is pre-orogenic, pre-deformation, pre-collision, post-continental extension. And sometimes you can observe here the gabbros cross-cutting by basaltic dikes. So you are sure that this sheared gabbro is before contraction, but it is cross-cut by basaltic dike on the bottom of the ocean of the ocean. Sorry. So uh, you can have continental oceanic continental core complex and oceanic core complex, able to exhume deeper rocks. Okay, in the first year, orogenic extensional tectonic was applied to rift continent, to spreading plates, but in the 90s it was applied also to thickened orogenic belt. So when driving forces are not more able to sustain the belt, you can build up by contraction the mountain belt. There is subduction, this is kind of movement, so the mountain grow and grow. But when the driving forces, compressional forces are no more active, there is a collapse of the thickened crust. And so this collapse happened by the activity of normal fault, low angle normal fault, high angle normal fault. So you have really collapse. And very efficient fault at the low angle normal fault. So normal fault with a shallow inclination, shallow dipping could extend the crust in very efficient way. Whereas nearly steep dipping fault are not efficient uh, to extend the crust. You need 100 or 1,000 of fault, but the horizontal extension is very limited. By a low angle fault, you can extend quickly large part of the code, so the collapse is much more efficient. Okay, this is a slide after Luca Menegon, who was visiting professor in Turin 2 years ago. He pointed out that in a mountain belt undergoes a continuous shortening, but it will not undergo thickening forever. You have to compress, but you have to build up a mountain belt such as 20 kilometers. We are not on Mars, whereas there is a volcano with the height of 20 kilometers, Monte Olympus, because there are some physical limits. The first one is the convergence rate between the plates, the strength structure of the lithosphere, and the density structure of the lithosphere. These three parameters are very important to put a limit to the general uh, growth of an orogen. And I can add also another factor that is not mentioned here. But if you have west-oriented subduction, the altitude of the belt is limited. If the subduction is to the east, there's much more support of the lithosphere to build up a big orogen such as the Himalaya or the Alps, according to the model by Carlo Doglioni about the asymmetric earth. Okay, if you like to build up a very big mountain belt, you have to increase the rate of convergence, increase the strength of the rock, introduce vertical force, lifting the rock, like reducing their average density by buoyance, they could build up. Anyway, it is not possible to grow the orogen infinitely. Sorry? The threshold, it depends on these parameters. It is not easy to assess a threshold uh, because you have to put all these parameters in the system to, yes. Usually in numerical models, you have to put these parameters because you have to constrain the rate of convergence, the rheology of the lithosphere of the upper crust or middle crust, and also you have to put the erosion, several such as the model by Jamez and Beaumont, take into account all these parameters, the density and the structure of the lithosphere. But you cannot have only one value because, for example, in the Himalayas, you have a big mountain belt like this. This is a nice picture. But also the rate of convergence change because before collision it was very fast, 17 millimeters per year. After collision, the velocity reduced a lot. Then you have some other things happened, the melting of the crust, so the density change, the rheology change. So it's a very different, complex task to put a threshold value. Okay. Okay, another about the mountain belt support. Increased topography will enhance the rate of exhumation within over-thickened crust by erosional processes. Increased topography will increase the precipitation. You know very well the monsoon, of course. And when after the collision, the mountain belt rise, and there was a change in the wind circulation all over the world. So there is a strong influence of the orogen in this kind of thing. You have slope instabilities, so land sliding and mass transport. This is very efficient all over the million years. And also, for example, in the Himalayan belt, we have the collision and the hypercollision indentation tectonics. So India is pushing towards the north, to Asia. So you have these are GPS velocities. You can see this direction. So this push in this direction, and material flow to the east or to the southeast, because helped by maybe strike slip fault, the Altin tag fault. There are many big faults helping to the material to move away from the Tibetan plateau. So just to have another view. Okay, we can go ahead by this. Uh, Also, the continental delamination during subduction. You have a delamination between the subducting lithosphere and this part. So the transistosphere could come in this part on this wedge. So you have an increase in temperature here, melting rocks. The rocks are weaker, so you can have a collapse of the crust. But we can go ahead. Okay, the lamination can cause orogenic collapse and orogenic root collapse because, of course, this part could detach from the other part. So you have melting, intrusion, and if maybe because if you detach this part, the isostatic could bring the rock upward. So it is another way to move the rocks to the surface. Uh, this should be happened also in the Himalayas, according the paper by Shemenda and others 2000. They proposed the initial steep subduction, then the lamination and the detachment of the lower slab. And after that, the lithosphere was more flat, as you can see now in seismic profile or in the model by proposed to exhume the Greater Himalayan sequence. Just this is a very simple picture, but you can see here the lithosphere is very flat below Tibet. But here you have ecologite rock. The Somorari ecologite is very, is very famous. So with a flat subduction, it is not easy to produce eclogite with ultra pressure metamorphism. And so you need steep subduction and then changing the angle of subduction. Okay. Okay, this is an example from this strange name, detachment zone, Norway. I'm not able to pronounce Nordfjordsson, maybe. This is a Caledonian Orogen. You remember the slide of the first day, Laurentia and Baltica to the west and to the east, they collided. There was a subduction of Laurentia below Baltica, the build of the Caledonian Orogen, then a collapse, extensional collapse is a beautiful detachment exposed in this part of Norway. You can see big porphyroclast, rotated porphyroclast indicated a sense of shear, some asymmetric Boudin along the same detachment, and this detachment causes the thinning of the orogen and the exhumation of the western gneiss complex. This one by movement, vertical movement. This movement is top to the west. And there is also a very important component of coaxial vertical shortening. So there is shearing, but also coaxial deformation is quite important to bring the rock upwards. Okay, as I already told you, uh, orogenesis induce climatic change by formation of climatic barriers, availability of materials to be altered and eroded, and superficial processes induce dynamic loading and unloading because, of course, with the rate of convergence, a few millimeters, few centimeters per year, you can, if you have erosion like the monsoon, active since 25 million years, you can erode, take away a lot of materials. And in this way, this movement, the movement here, we are in the Himalayas, the South Tibetan detachment is a normal fault with top down to the north sense of shear, as you know. The main central thrust is a thrust sense with top to the southwest sense of shear plus movement. So this arrow bring this part upward. In this model by channel flow, we will come back later on this. There are also molten rocks and migmatites that are, moving in this direction. And if you have mm, efficient erosion in the frontal part of the belt, you can move this rock continuously. So this erosion helps to exhume the rocks. But it depends where the rock are going. If the rock are deposited in the foreland basin, and you have a thick sequence of rock here, you increase the lithostatic pressure here in the main boundary thrust or the frontal thrust. So there is no, you are not able to move this rock towards the Indian foreland. But in the case of the Himalayas, most of the sediments are transported in the Bengal fan. That is a very huge fan. The thickness is up to 12 kilometers, and the length is more than 1,000 kilometers. So you can put away the sediments from the belt, so you can move this rock with no big problem. In some numerical models that we made by Andrea Piccolo, Emanuele Faccenda from Padua University that they published maybe in 2018. We try to mm, modelize, to make numerical models of the Himalayas to explain this feature and also the mid year zone that we discovered a few years ago. And in these models, we found that without erosion, there is no efficient exhumation of the rocks. And also, if you accumulate the eroded materials in front of the belt, you can you cannot shear efficiently, but you can create a lot of folds in the frontal part. And also, if erosion is shifted in some other part, you can affect also the formation of nice dome here or in the other part. So erosion is not the main mechanism, but it modulates the kind of deformation and of the overall geometry of the belt. But we'll come back a little bit later on this mechanism of channel flow because it has been applied for several years and several times in the Himalayan belt and also in some other orogen. Okay, we come back a little bit to the Variscan belt in Europe. You can see Sardinia and Corsica rotated in the original position um, before alpine orogenesis. If we give a look to this part of the France, the French Massif Central, there is this structure that's named the Montagne Noire, means Black Mountain in France. This is a field trip a few years ago with some people. You can see Jordi Carreras, Michel Balevre, mm, and some other famous people working on the bottom of the Variscan and the Alpine tectonics. And this was important place because Malavieille, Jacques Malavieille, Michel Faure, two French geologists, applied for the first time the concept of core complex or extensional collapse in an orogenic belt, because up to that that time, sorry, people believe that extension is before mountain belt, then contraction, and stop. They studied this huge anticline, that is the Montagne Noire, a nice place. You have gneisses, Paleozoic gneisses, migmatites, granites, and these rocks are surrounded by schist and mica schist, and then these light blue, are low to metamorphosed Paleozoic sedimentary rocks. So you have a cover of non-metamorphic rocks and a core of metamorphic rocks with migmatite and Paleozoic granite. So the classical cross-section is like this, is subduction, the frontal thrust of the belt to the south, this huge antiform surrounded uh, by uh, this black line that people recognize to be a myelonite. So they proposed the application of a core complex after collisional tectonics. So you have to seek the crust by collision and then collapse by recurrence of a core complex is a huge malonite deformation here, brittle deformation above, uplift of this and exhumation of these rocks. This was in this paper, it was very important because they changed the thinking of people about the orogens. So at that time, orogenic complexes were only applied to essential tectonics. In this way, they are coupled with um, orogenic contraction. Okay, now this is the post-orogenic extension, but another very important mechanism is the synconvergence exhumation. So, of course, you have to thick the crust by contraction, then collapse, and the rocks are uplifted or exhumed, so no problem for this. But another important mechanism is the syn convergence exhumation. So rocks are exhumed during convergence, during the formation of the belt. The first paper pointing this was by John Platt in 1986. He proposed this mechanism to exhume high pressure or ultra high pressure rocks because extension by core complex was not enough to justify the exhumation of his so deep rock. So I think he proposed the corner flow of low viscosity material. Corner flow, you are in this situation, you are um, in a wedge, orogenic wedge. So material can move in this direction. Corner flow means you reach this part and then you come back. You you have a buttress like this, and the rocks are exhumed because they cannot go in this direction, but move downward and upward. Corner flow means this movement, and for that it is enough to exhume high pressure rocks. You can see maybe the scale 50 kilometers, 60 kilometers, but it depends. This is applied to the Franciscan complex in USA, but okay, this a general view or particular way, it's an evolution of this one. Okay, and he proposed also the occurrence of normal fault extension on top of the wedge, because if you bring materials below here, the wedge increases in thickness, and if you have uh, the velocity fixed, the density of the rock fixed, the pressure of fluid. He calculated several physical parameters controlling the geometry of the wedge. If you add materials below, you can increase in thickness. And to maintain the stability, maybe the sum of this angle plus this angle. The shape is fixed and is controlled by the dynamics of the formation. You have to start to form normal fault to maintain the critical taper, the critical geometry of the wedge. So there's a possibility to have extension during convergence, sync convergence extension. If you add material in the frontal part, the wedge lengthen, so you have to contract to shorten a little bit, and you can give rise to out of sequence thrust to come back to the original shape because it is an equilibrium shape. So this is more or less. So the most important thing for our um, topic is that extension may occur in the upper part of the accretionary wedge, thickened by underplating of material from subducting plate, or may affect the lithosphere in a region of intercontinental convergence if surface elevation has been increased by the removal or lithospheric route. In the second case, extension may be accompanied by magmatism and an evolution towards higher temperature during the compression of the homomorphic terrain. So at this time, no people observed this kind of extension. It was just a theoretical model, but we have to remember that Jean-Pierre Bourg and the French people recognized the South Tibetan detachment on top of the Himalayan belt, but it was not yet involved in this tectonic model. But just 3 years before, he proposed the occurrence of this detachment on top of the belt. It was the first paper pointing the occurrence of extension during contraction. And this is a nice analog model by experiment made by Jacques Malaviel or Chemenda in the 90s, in 2000. This is one of the first experiment by Chemenda in 1995. They proposed, of course, a situation like the Himalayan belt, but very simplified. Area, India, subduction, and this part is very light, going to subduction. Buoyancy of this part started to detach these rocks from this part, and these move towards the higher part. In this picture, you can see a little bit better the explanation. The crust is here. Buoyancy started to break the rock, the lithosphere in this part. So going down, buoyancy force increases. So the material is pushed upward. So to push up toward this material, you have to have a thrust here, that is a bend-center thrust, and moving in this part, you need to have a normal fault on top. It is just the main central truss and South Tibetan detachment. It was a very nice model. After that, of course, you move towards the foreland more and more. You can have also backtrusting, molasses, and so on. But it was very important because for the first time, I remember some international conference in Europe where the people, Chemend and Malavel, presented these models were very popular because for the first time they were able to explain exhumation by sync convergence extrusion. So you have to exhume this rock during convergence, the contraction, by extrusion of this material. Material is extruded, is pushed upward during convergence. And this is a very nice model because it has been applied also in several, many others orogenic belt. Of course, sometimes people forget that you need not only the thrust, but you need also the normal fault on top. So I see there is also a model published 1 or 2 months ago in the Western Alps where people propose this mechanism of exhumation of ultra high pressure rocks, but they forgot to testify the occurrence of normal fault on top of the unit. It is very important because the thrust is very common. You have thrust everywhere in mountain belt, but you need to have the thrust at the same time of the detachment of normal fault. They should be contemporaneous, because to move this stuff upward, you need the thrust here and detachment here, but at the same time, or also little bit different time, but this should exist and they should prove the occurrence by testifying myelonites, kinematic indicators, and the right kinematic indicator, because sometimes people publish picture that are not convincing about kinematic indicators, even in the last month or year. So it is not. Mm. Okay, this is not really an extensional fault. It is what dunque, means called this I forgot the name, stretching fault, because I think it is possible to have a normal fault. You can move the hanging wall downward, or you can fix the hanging wall and move the foot wall upward. This kind of fault are named stretching fault. The apparent movement is extensional. It is extensional from the geometry kinematic, but you not have an extension of the crust. So it's an important point because you have not extensional collapse on top of the belt during the detachment formation. You have a normal movement induced by the upward movement of the greater Valiant sequence. Yeah, yeah. Oh, okay. Nice observation because you have a lot of leucogranites, Miocene leucogranites, just confined in the upper part of Greater Himalayan sequence. The Napsi Pluton, the Mount Everest, Makalu are very big intrusion. One explanation is the melting by decompression. You have hot rocks, you make a decompression, so the hot rock melt, and by buoyancy they go upward and make intrusion, dikes. Is one of the possible explanation. But there is surely a strong connection between the detachment and the granites, because they are all along the detachment or just below. And this is also very important because this kind of mechanism may be may cause the enrichment of lithium, rare earth element that are very useful for this kind of transition in energy. So Chinese people is studying a lot this leucogranite because large part of the leucogranite crop out in China, in Tibet. So it is quite easy to reach the places by roads, and they are studying this rock a lot. And also in the North Himalayan gneiss dome, there are a lot of leucogranites like the one that we can observe here. If we come back to the picture, to this picture, you can see here the South Tibetan detachment. Now, most people think that the South Tibetan detachment is folded here in the North Himalayan gneiss dome. So the Greater Himalayan sequence is just here and here. So the same metamorphic rocks and the same granite drop out in central part of Tibet along this alignment of Nice Dome. Okay. Okay, after the model by Malaviel and Shemenda, uh, people start to think about the situation of the Himalayan belt. In this very simple sketch, you can see the first application of this extrusion because you can see the Glitterman sequence. Uh, Most people think that South Tibetan detachment and main central thrust merge into depth, but there are also some paper by Alexander Webb that show that the merging is towards the foreland, just as in Sutleji area. So could be this shape, or this one. So it depends on the section. This was caused by the physical model by Nelson and others in 1998. They proposed the geophysical section in the eastern part of Himalaya, where maybe sometimes the situation could be similar to this one. Anyway, the activity of South Tibetan detachment and Mensa Trust could cause the extrusion of this part. The first model proposed the grid Himalayan sequence as a solid piece of rocks extruded without internal deformation, but so it's a rigid body. But after people started to think about that there is a deformation inside, so a lot of minor shear zone inside with folding maybe of the isogrades. You can see inverted the main central thrust and a normal isograde along the South Tibetan detachment. So this a little bit more real model. After that, people recognize that the deformation inside the Grit sequence is made by non-coaxial deformation. This means that you add simple shear plus pure shear with a kinematic vorticity in between 0 and 1. We made some measurement of vorticity in Bhutan in Grit sequence in the central part because a lot of people concentrated here and here. And in the several years ago, like 2005, 6, I don't remember, we found a lot of pure shear in the central part of the Gregorian sequence and an increasing simple shear component towards the main central thrust and towards the higher part of the South Tibetan detachment. So this is a much more natural kind of a deformation, general shear or non-coaxial deformation within the Greater Mayan sequence. Last model in this picture is the channel flow model, in which the greater Himalayan sequence has been regarded as a low viscosity channel. You have a partial melt zone, migmatites, moving to the south and towards the surface. This has been proposed firstly by Gruitz and others in 1996, 2002. Then it was modelized by Beaumont and James in 2001, the Canadian geologist, and Beaumont is a geophysicist. And in this book of Geological Society of London, by Gooden and others, I applied a lot to this kind of model. So this was a dominant model for several years in the Himalayas. It was very nice, but not real good to apply to real rocks. Okay, one of the most important thing to apply extrusion or channel flow is to have a thrust at the base and a normal fault to the top, but they should be contemporaneous. And the people, such as Godin and others, put all the ages found all over the Himalayas of the main central thrust and South Tibetan detachment, and they found a concentration between 10, 25, 23, and 70 million years. And for them, the activity of these two big faults was contemporaneous in this time span. Okay, this is a picture of the Himalayas at the altitude of Kathmandu. This is a Kathmandu clip, not very different from the Jutog clip that you know very well here. Uh, the grid terminal sequence, the main central thrust, the gneiss, and the granites concentrated just below the South Tibetan detachment. So the compression should be sure an important component in melting these rocks because um, people found evidence that leucogranite originated from the melting of the great remnant sequence and then migrated upward by plutons or by dikes. And I will show you the Makalu section. It's a very beautiful exposure where all the naps you can see in the lower part gneisses with a lot of dikes. Then they merge and made the main Pluton of the Makalu, Mount Makalu. So just in the field, it is evident this kind of origin. Okay, if give a look to the channel flow model. Channel flow model is very interesting. I was fascinated by this model in the first years because uh, in this model, a low viscosity fluid flow in a channel between two rigid plates. So you have two rigid plates like this. This is a grid Himalayan sequence. So you have here the detachment, and here the main central thrust, normal fault, main central thrust fault, and this deformation is caused by two kind of deformation. A different in pressure because we have high pressure here below the Tibet, the Tibetan plateau, and the lower pressure here in the frontal part of the belt. So if you have a fluid here and here there is a higher pressure, lower pressure, you cause a flow in this direction, like a pipe. If you go in the water flow in this direction. And the velocity distribution due to this pressure gradient is like this, a parabolic shape. So this the velocity is very low and increases in the central part, then decreases up to the main central thrust. The second the second factor is a quiet flow. It is a name that indicates the simple shear because we are subducting the Indian crust. So you have a simple shear like this. So little displacement here, a large displacement in the part. So you have to sum up these two components and you sum the vectors of course here in a qualitative way, but in the paper by Turcotte and Schubert, in the paper, a book, they make calculation and also James and Poumont calculated the result of these of these two components. You can uh, you can see that in this part, since these arrows are very short, these arrows are dominant. So the resulting is a movement of this upper part to the south, whereas in this part, these arrows are longer and they are of course inverted. So in this channel, by these two components of the formation, you have the lower part underwent burial and the upper part underwent exhumation. This is very nice because during subduction convergence, you cause the upper part of greater remnant sequence to be exhumed. So, but you need, of course, a rigid plate above, a rigid plate below. So you need to confine the melt in this part. This is a limit of the numeric model because you force the model to work in this way. So if you change the parameters of density in these rocks, the result is completely different. And with um, Manuale Faccenda and Piccolo, we changed this kind of things and we obtained the different results, very similar to the Malayan belt, but with no channel flow, but with other uh, deformation mechanism. It was a long work because they made the master thesis and they made 130 model, and each model needed 2 days of working with supercalculator. So very long time, but it was very nice. Okay, we come back also on the channel flow model. Another very interesting and new model of exhumation is the distributed ductile thinning that is maybe come from the McKenzie model of the extension. You remember one of the first slide that I showed you before. Come back quickly. Ah, okay, this one. The McKenzie model, you apply pure shear to lithosphere, so this part is thinned, and you have lowering in pressure, so exhumation. But it was not so explicit in this model. But after a lot of years, okay, Con Long, that is a American geologist working in the Himalayas, especially in Bhutan, applied this concept to the Greater Himalayan sequence. And so maybe you can have different exhumation processes that operate during orogenesis, maybe erosion. So by erosion, you have a load. By erosion, the load is decreased. So the final pressure P1 is lower than the initial pressure P2 is lower than P1. Also normal faulting, remove material from above, so the final pressure is below, is lesser than initial pressure, but also distributed ductile thinning can cause a decreasing in pressure. The final pressure is below, is lesser than the initial pressure because you can see this grid that was proposed by Rick Lowe several years ago. It's very simple, but you apply your shear, you have to thin this part and you cause extrusion in this side and extrusion in this side, but, such as jam between toast. Okay, you press the toast and the jam go away from each part. Of course, if you are in orogenic belt, maybe if it is the Greater sequence, we can push the material upward because the pressure is low, but you cannot put the material downward because the pressure is increasing. So you have to extrude to push the material upward. Apart this, okay, so if the volume is conservated, you thin this part, you enlarge the material in this direction, enhanced by transport. So in this way, you can also exhume material. And the deformation, of course, need to be pure shear plus simple shear. Mm. And as I made some calculation, this is a paper by Long and Datter 2021 on geology. They studied the Bhutan, central Bhutan, and central Nepal. Is the peak pressure of the rocks of the Guitamarian sequence is this color, the reddish color. Um, so is the structure distance above the main central thrust. You are very 10 kilometers from the main central thrust. You are at the level of main central thrust. The pressure is 11 kilobar. Also here 10, 11 kilobar. Going upward, the pressure decreases up to 4.5 kilobar or 3, 4 kilobar. So they made a lot of calculation and they compared the lithostatic pressure, this one, this dashed line, with the calculated pressure by thermobarometry, normal thermobarometry in the rocks. And at the end, they found that the normal lithostatic pressure, lithostatic gradient is morely 0, 0.27 kilobars or 0.3 kilobar, increasing of pressure in the normal crust. After the thinning, the lithostatic pressure, the gradient was 0.6, nearly 0.6 in Bhutan and 0.6 in Nepal. This means that as a result, a little bit complex calculation, but in the paper is explained. This example define up to 10, 15 kilometers of exhumation, so nearly 3-4 kilobars of decompression of the rock near the base of the synod interval, so at the base of the altitude of the main central thrust, entirely as a result of the distributed tile thinning. So this mechanism account for up to 33-50% of the total exhumation part of these rocks. So it is not a secondary mechanism of exhumation, but we have to take care of also this mechanism in explaining the exhumation of the rocks of the Greater Marine Belt or other situation similar to this one. So the concept is quite easy because you decrease the total weight, the total pressure by thinning the ductile part. You thin this part and you extend in the direction. So this thinned part is 1/2 of the original thickness. So there is a consequent exhumation. Okay, the last mechanism is the exhumation by transpression. If you go from the upper part of the crust to the lower part, in the upper part of the crust, you can have a transpressional fault, that is a flower structure that you know very well, the brittle deformation. But if you go downward, this deformation that is caused by uh, simple shear and pure shear, like we can see here, you can see this orange block and this orange block are displaced in a dextral way, but there is also a component of shortening perpendicular to the shear zone, so you have a vertical extrusion. The green block inside is growing in a vertical position. It cannot grow downward because of the pressure. So if this is maybe 50 kilometers, you can explain exhumation of 20, 50, 20, 30 kilometers, depending of the dimension of the volume of the block involved in transpression. So it is another way to explain the exhumation. Of course, in this kind of ductile transpression in the middle and the lower crust, you need to have simple shear and pure shear. So the deformation is a general shear with a vorticity number between 0 and 1. So if you take a measurement of the vorticity in these rocks, you have to find these two components of the deformation. Okay, make a stop, 10 minutes stop. Okay. And then we started to speak about the Variscan deformation by transpression. Okay, we can restart. Thank you. Now we'll speak about the East Variscan shear zone in the Variscan orogen in Western Europe. That is a beautiful example of a regional scale shear zone studied by different uh, ways, testifying the exhumation by transpression in the Carboniferous time. As I showed you before, the violet rocks are the Variscan, the Paleozoic rocks in Europe, affected by the Variscan orogeny, the older orogeny than the Alps and the Apennines. In some part of the Alps, you can observe these basement rocks deeply involved in the deformation, the metamorphism, such as the Doria Maira, where quesite was found in the 80s inside the garnet in the continental crust. In southern Italy, you can see also basement involved in Sicily, in Tuscany. So in these areas, it is very difficult to recognize the deformation of the Paleozoic age because it is transposed and affected by later metamorphism and deformation. But if you go outside the Alpine or Apennine, maybe in southern Corsica or Sardinia, on the more Esterel, in the French Massif Central, uh, Brittany, and so on, you can observe the rocks without many further deformation. So you can study a little bit better what happened at Carboniferous time. The Variscan belt is not a linear belt, but is made by two orocline. That is the curvature of the orogen. The most famous and the bigger one is the Ibero-Armorican arc. Take the name from Spain and Armorica in northwestern France. And there is also another smaller orocline in the eastern part, this one, that is bounded to the east by this line that is East Variscan shear zone. It is a ductile shear zone um, running for several hundred kilometers. And we can find this shear zone well exposed in Sardinia, in the Morse Esterel in southern France, in Argentera Massive, in Aiguille Rouge, in this external crystalline massif in the Alps. So this is just the actual position of the East Variscan shear zone that, of course, before the rotation of Corsica and Sardinia was put in this position, more or less, in this direction, the original one, because Corsica and Sardinia rotated counterclockwise 21, 22 million years ago during the formation of the northern Apennines. Then Apennines rotated in this way, and we had the opening of the Tyrrhenian Sea. Okay. Mm. Thanks. Thank you very much. Oh, thanks. Yeah. Okay, this is just a simplified geological map of the Variscan basement in Sardinia. It is just a small piece of the whole orogen, but there is all. You can see here in this part the external zone, the foreland. This is the so-called NAP zone. There are a lot of tectonic units superposed or NAP made by Paleozoic rock from Cambrian to Upper Devonian. This red line is the strand of the Est Variscan shear zone. After that, we have the inner part of the belt with a lot of granite, this one, and high-grade metamorphic rocks with migmatite, gneisses, and so on. Just to have an idea, the collision formed during the lower Carboniferous at 350, 340 million years. We have a Barrovian metamorphism that is prograde from southwest to northeast. Here we have very low grade, green schist grade, upper green schist grade, amphibolite facies metamorphism, and high-grade metamorphism. Close to the east Variscan shear zone, you have metamorphic minerals such as kyanite, starolite, garnet, very, very close to the shear zone. There are a lot of magnetic intrusion. You can see this violet stuff. Very few in the south, very large intrusion in the north, and also in Corsica there are a lot of granites, many granites associated with migmatites. The tectonic transport of the NAP moved from the northeast to the southwest, from the hinterland to the foreland. Just to geological cross-section made in southern France or in Sardinia. You can see the main body of the Pluton included at 290, 330 million years. They cross-cut all the foliation, metamorphism, and so on. You are here in the internal zone with migmatites. This is the shear zone, dipping a little bit to the south. Mica schist and gneisses here. And here we go to the NAP zone with the tectonic transport to the southeast. More or less the same is in France. You can see it is a main tectonic transport to the south with thrust and so on, and a back deformation with folding and thrusting to the north. So the first phase during collision is top to the south. Second phase during transpression or later deformation is top to the north. So backward the deformation. You can see metamorphic mineral chlorite for 1,000 kilometers. Then start a few kilometers to the south of the shear zone biotite, garnet, starolite plus biotite, kyanite plus biotite, sillimanite and feldspar with the occurrence of migmatite, and these yellow stuff are eclogites formed during subduction of the Paleozoic ocean. You can observe that the metamorphic isograde increase decrease the distance approaching the shear zone as in the same way that what happens in the main central thrust of Tibetan detachment. We have a telescoping of the isogrades due to deformation. It's just a picture from the paper by French people, Schneider, Gerbold, 2014, 15, and 17. They propose also numerical model of the orogen. You have the southern continent extension during the Cambrian Ordovician, subduction of the oceanic lithosphere, the collisional stage, propagation of deformation to the south, to the foreland, back deformation by folding and thrusting, and appearing in the inner part of the belt, more or less just to have an idea. About the ages, there are some small differences because some data increases, so some little differences are found, but the general picture more or less is correct. In this synoptic view, you can see the main orogenic feature. You can see the timing here. You have subduction more or less during the volume. It is not well dated, but more or less it should happen in this time span. The thickening after collision is more or less in this part. Then transpressional tectonics, and then post-collisional extension. About the deformation, we have some datings of deformation. So B1 deformation is referred to the thickening stage, more or less 340 million years. The transpression is well constrained, and it is called the D2 deformation in this picture. And the age was more or less 320, 350 milliyears, but just in Sardinia. Metamorphism, eclogite facies, granulite facies, amphibolite, and high pressure, low temperature metamorphism with the growth of andesite, cordierite, biotite in a static manner above metamorphic minerals, other metamorphic minerals and deformation. The intrusion, the oldest intrusion have been found in Corsica, 340 million years, and they are of course deformed by the collision. Other intrusion is 322, 2095. Of course, these show a little bit deformation. This one are completely isotropic and cross-cut of the structure of the bed. Just to have an idea, since it is very far origin. Okay, the shear zone has been studied in several transects in Sardinia, the Mors Massif, in the Argentera Massif, and in the Aguirre Massif in the Western Alps. Here's a panoramic view of Sardinia. These are late Variscan granites. Here we have kyanite-bearing mica schist, migmatites, and more or less this part is affected by the Variscan shear zone. In the same way, we are in the Argentera Massif, that is a nice mountain between France and Italy, with a lot of mylonites, several kilometers of mylonites, and migmatites in the French side. Okay, in these outcrops, huge outcrops of kilometric width, we have a vertical foliation, vertical myelonitic foliation, shallow dipping or horizontal mineral lineation, like a strike slip formation, but not really horizontal, but shallow dipping. So the geometry of the shear zone is more or less the same in all these outcrop. The kinematic is more or less the same, as we shall see, and we gained also the time of the shearing event by the same methods. In this diagram, you can see more or less the delineation or that is more or less the same all over the outcrops. So there is the geometry and the kinematic is very constant. About the sense of shear, you know this in section I show you last days. We have here a picture of Ordovician orthogranuluritic orthognesis made by quartz feldspar biotite. You can see this geological hammer. You have a beautiful S and C structure affecting the orthognesis. It is very nice because if you go kilometers away from this outcrop, sorry, the granodiorite become less and less deformed. So the formation increases towards the northern part of the Sardinia island with a well-developed S, C, and C prime structure, pointing to a dextral sense of shear. The foliation is vertical and it is dextral sense of shear. In thin section, you have, of course, biotite fish or foliation fish is also SC structure, and the sense of shear is absolutely the same. And also in the more massive in the Argentera, absolutely the same beautiful kinematic indicators, no difference. Okay, so we try to characterize also the kinematic of the flow, and we gained information of the age by petrochronology using uranium, thorium, lead on monazite, because we found a lot of monazite inside the metamorphic rocks, and the monazite is very useful to date the formation. especially if we use the chemical composition of the monazite. It is a small crystal of monazite, is 400 micron. This crystal of monazite has been analyzed by electronic microprobe to detect the amount of yttrium, lanthanum, rare earth element, and there is a clear zoning, for example, in yttrium. The core of the monazite is poor in yttrium, whereas the rim is enriched in yttrium, the red color. These red dot are uh, the point where the laser ablation gained information about the ages. More or less, the spot is 10 microns thick. So we use the monazite along the main foliation, the malonitic foliation, and also monazite inside a garnet crystal close to the rim. In this way, we can use a laser ablation dating the core or the rim, and they gave different information because I don't remember if I put. Okay, because for example, there is a zoning of the monazite. This monazite came from the Argentera massif. The blue color means that there is a low amount of yttrium inside. And if you give a look to the spot, this spot is 342 million years. The red spot, the spot in the red part, more or less is 340, 340. Okay, is a little bit different. We are in a proto-myelocyte, so we found this monazite in the proto-myelocyte, and the core and the rim give more or less the same age, 340. In the monazite, in the myelonitic rocks, the strongly deformed rocks, we found ages in the core at 336, and in the rim 322. So there is a difference between the core and the rim of several million years, but we also need to give a look uh, to the core. Usually, low amount of yttrium is related to increasing metamorphism, whereas a lower amount of yttrium is related to the retrograde metamorphism. So it is just a very important proxy for metamorphism. This monazite in the Argentara Massif is very nice because it is big, 100 microns, so you can see the naked eye in the scene section. So the picture is not complete. It is interesting because you can observe the higher yttrium parts here and here, like in this part. You remember the ascensional site in the quadrant of the formation? It is exactly the same. Means that you have monazite like this in the proto-myelocyte with this kind of sense of shear, and yttrium is enriched in this part. So this means that this yttrium, this part grows during the formation, during the formation. So if I date here, I am sure that it is a thin kinematic crystal growing during the formation. It is very important because when I date small tiny minerals, I have several numbers and it is difficult to relate the age to some event, some event. In this case, I am sure that this geometry of the enrichment in yttrium is related to the shearing. So the proto-myelocyte is 340, the myelocyte is 322, just these two examples. Of course, we analyzed a lot of crystals, so the age of the formation should be more or less 330, 340 in the proto-myelocyte, so we extended also the shearing at the map scale. And the myelocyte age developed 320, 315 million years. Of course, we can use also the rare earth element in monazite, showing that rare earth element increase towards the younger ages. because there is also retrograde metamorphism. So it is a good indicator. Okay, coming back to Sardinia, we made more or less the same with the same methodology. We this was made by the PhD thesis by Matteo Simonetti that worked in the field in Morse Massif, Argentera, and the Rouge, and analyzed the rocks in the California at the California University with John Cotter, that is also a very famous worker in the Himalayas. So the methodology absolutely is the same, and the instrument is the best in the world. So the data is are very good. Okay. And to gain information about the kinematic of the flow, that is to say the vorticity analysis amount, that is amount of pure shear, simple shear, we use the different approach. The first one is a more simple, is to use, okay, I need to explain a little bit what happened, because more or less in simple shear, in pure shear, you have a deformation like this, and the flow of the particles is like this. So the particles move in this direction, and in this direction. So when you deform a circle to become ellipse, you have this kind of movement. So every path follow a parabolic shape, but only two perpendicular lines are straight. These are called apophyses of the flow. Okay, this is in pure shear. In simple shear, the situation is a little bit different because these two apophyses, this is a stable one because it is more or less parallel to the shear plane, but this one rotate, moves in this direction with for example, with the dextral simple shear, and it is very interesting because they are mm, related to the amount of vorticity because this angle alpha, is related to the amount of pure shear and simple shear. If you put these two amount together, pure shear plus the simple shear, these apophyses rotate towards parallelism, towards the stable apophysis, this one. In simple shear, you have only one apophysis and all the materials move in this way or in this way. So this is the starting point from pure shear, and simple shear on only the stable apophysis. This angle is related to vorticity. The vorticity number is more or less the cosine of this angle. Another important thing that some people discovered, such as Kurz, Northrop, Illiam, and others, that C prime, the famous C prime that we used for kinematic analysis, is more or less dividing this angle into equal parts. So if I take a mm, measurement of this angle between the foliation and the C prime, I can estimate the vorticity. So it is quite simple because I can use this method also in the field because I see correctly the C prime. And so using this angle, we calculated more or less the amount of simple shear and push shear. Another method that we use that is quite easy is the stable Porphyro class method developed by Wallis and Pasquier in the 80s and the 90s. This means I will explain maybe the day after tomorrow a little bit this method, but during deformation you have a rotation of rigid object for example, in simple shear of the object that rotate in this direction. But if you have a rounded object, they rotate continuously during the formation, such as the porphyroclast making delta type tails. If you have elongated porphyroclast like this, they rotate but become stable more or less parallel to the flow plane. So if you take measurement of the long axis and the short axis, long axis, short axis, and orientation of the long axis, you can put in a graph like this with the axial ratio, sorry, this angle alpha, this axial ratio, and if you have a large number of porphyroclast free to rotate in the flow, you have in this part the more or less rounded porphyroclast that rotate continuously in between 90 degree and minus 90 degree. You have, of course, to take measurement in this way. The axial ratio is maybe this 1, 2, 3, 4. So the rounded objects are positioned in this way and are and show all the possible orientation. The elongated porphyroclast stabilized in this position because they rotate and are stable parallel to the foreplane. So at the end, you have two populations of porphyroclast, the one that show orientation in every direction and the one that are concentrated in maybe between 5-10 degrees or nearly parallel to the and this division is characterized by an axial ratio that is a critical axial ratio, and the vorticity, it is just related by a simple equation like this. Axial ratio plus 1 elevated to 2 divided by this one. So it is very easy to calculate. The most important thing is to have a large number of porphyroclast with a lot of difference between rounded porphyroclast and elongated porphyroclast. So you have to put in this kind of graph all your porphyroclast, and you will be able to separate these two fields, continuous rotating or stable porphyroclast. Usually in this part you have delta type porphyroclast, and this part you have the sigma porphyroclast showing lower rate of rotation, as I remember from yesterday. Okay. Okay, so we made this kind of work in several scene section. You can see the graph with the axial ratio here, the orientation here. You can see a lot of point. This part is related to continuously rotating object. This part, the posterior cluster more or less parallel. We use Garnet and Fespar. There are more or less 400 posterior cluster in this graph. And by this critical axial ratio, we found vorticity. Just these are quite easy. The third method that we used was used by Matteo Simonetti, and he worked a lot with Rick Law in Virginia Tech University, because Rick Law is very expert in quartz analysis and microfabric. Is to use the oblique foliation in quartz. So you have to take a lot of measurement of the shape, grain, preferred orientation in oblique foliation, and also to take measurement of the quartz c-axis, and to plot in a stereographic projection. In this way, you can gain information about the temperature of the formation, but also on the vorticity, on the amount of shear. It is not really easy if you do manually, but if you put the scene section under the electronic microprobe with a backscattered analyzer, you can have a whole figure of the crystal, make more or less made automatically, so you can interpret this diagram with, without losing much time. So in this way, so we gained information of vorticity by these three methods. It is important because vorticity is affected by several factors. Maybe when you use porphyroclast, of course, you have a porphyroclast that is cut in the central part. Another one is cut in the external part. So the axial ratio is a little bit complicated by this. So just the cutting effect is important. So the measures that you gain from 0 to 1 are not so precise. You cannot see 0.32 is different from 0.33. You have to give just an idea, but it's important to compare different methods to have more or less the same result, because only one method may be a little bit dangerous. For example, the porphyroclast could be one close to each other. The C prime could rotate because when you form a line, they rotate to parallelize to the shear plane, so it is not a really stable position. So there are several things affecting the deformation. Also, quartz is very nice, the method, but quartz is very sensible to deformation because at 300 degrees it recrystallized. So you cannot record the complete history of the rock by quartz, but only the final stages. Whereas porphyroclast record maybe all the deformation history, but it is less precise. So you have to mix all the information uh, more or less to gain numbers that has a little bit meaning. Okay, this is trend of the Variscan shear zone in Sardinia. The shear zone is just in this part. The scale is 200 meters. The thickness is a few kilometers. We took sample in this part, in the yellow part, where there is a staurolite and garnet bearing mica schist. These Arcanite mica cyst and the granulorite orthognesis. In this mica cyst, we found staurolite along monazite along the main foliation inside the garnet. We analyzed by electronic microscope. We made a map of yttrium, thorium, and other rare earth element, but the most important is yttrium and thorium. And we gained ages 310, 319, 330. So we analyzed a lot of this kind of monazite with a laser ablation. So laser ablation is very important because you can choose exactly the point that you would like to date, the core, the rim, the amount of yttrium. But of course, you have to know very well the structure relation of the monazite with respect of the foliation, if it is growth along the foliation or rotated, or if it is inside the garnet or the staurolite. So you have to characterize very well. In this way, the core of the monazite is it is depleted in yttrium, the blue color, indicate a more or less increasing metamorphism at 350, 340 million years, up to 330, before transpressional deformation. And transpression was constrained by the high yttrium rims, more or less the reddish one, at 325, up to 300 million years. So a little bit later, and this age is more or less in agreement with other findings, such as the one in the Western Alps, Argentera Massif, so a little bit to the north. and a little involved in the alpine orogen, but not so much. Only a few very low-grade metamorphism and some brittle thrust. So the Variscan history has not been affected. But this shear zone started before, started 330 million years. So maybe 5 million years before the Posada Asinara one in Sardinia. Okay, this is just a picture that we published maybe 2 or 3 years ago. This representation of starolite bearing mica schist in Sardinia, monazite in several position. So if you have several position of monazite, maybe monazite along the S1 foliation in the starolite, this is just a thin section similar to the one that explained yesterday with Boudinage. So this is should be related to collisional stage. This to the beginning of shearing by transpression. This by transpression. And so if you gain age and the structural position and monazite content, you can constrain the D1 event, the collisional one, with the inner part of the monazite depleted in yttrium. The D2 event when the monazite are reached in yttrium, especially in the rim, and the D3 event when monazite is destabilized and became allanite at 550 degrees more or less. So just this picture is good. It recall all the observation that we made. So more or less, the end of the D1 deformation is 330 million years. Of course, this part of the PT path is lacking because it has been erased or cancelled, and only information remain inside the porphyroblast of garnet, of starolite, and sometimes of albite. Mm? Uh, so we have information about the D2 deformation, that is this part of the PT path, the compressional one, is very important because along this foliation there is a decompression. Of course, we have also PT constrained by petrology or classical T analysis or isochemical pseudosections, the most modern one, and also the last part of the deformation where the rocks underwent exhumation and heating in the Andaluzite stability field. In fact, in some places we can find a big crystal of Andaluzite growing statically above the metamorphic Barovian metamorphic minerals and transpressional foliation. It's very important because to this moment, people believed that this foliation was related to the collisional of the two continents, whereas we pointed out just in paper, maybe a lot of years ago, 2002 or 2024, we pointed out that D2 deformation was related to exhumation with a decrease in pressure of several kilobars during shearing. Mm. And by vorticity, we pointed out that deformation is characterized by vorticity number. This is push shear and simple shear. Okay. Uh, all sample fall in this part in between 0.35 and 0.75. So we are in a pure shear dominated transpression. So there is a component of simple shear, but it's not the dominant component. The dominant is the pure shear. It is very important to extrude the rocks. These are a different graph. The percent of pure shear and the vorticity number, our sample fall in this part. The 50% of simple shear and pull shear is just at 0.71 in this position, because it is not a linear relation for this one. This graph is nice. It is from Fossen, Fossen 1993. You can put vorticity and the angle between the instantaneous stretching axis maximum and the shear zone. This is a shear zone, this deformation, this is a instantaneous stretching axis. That means the elongation of the incremental strain. If this angle is below 45 degrees, from 45 degrees to lesser one, you are in a transpressional deformation. If this angle is higher than 45 degrees, you are in an elongate situation, so in transtension. So you are in this upper part of the graph. There's another way to represent transpressional deformation or transtensional. These are some results of the C prime measurement that we made in scene section. Is a stable apophysis, the moving apophysis depending on the amount of pure shear. So we calculated this angle. So also this one, and the vorticity is the cosine of 2 times this angle. So quite easy and quite easy to gain information. By this method, we obtained also a pure shear of 75%, also in transpressional deformation. So there is an agreement between between these two methods. This is a map of the vorticity, the distribution of the vorticity value in the northern part of Sardinia. We are in the northeastern part. This is more or less the high strain zone of the Posada Avinara shear zone, the Est-Variscan shear zone. We have some sample, and we made a map instead of a single section, and we can more or less observe that vorticity increases towards the high strain zone. This means that in this part we have a lot of pure shear, and the simple shear increases approaching the high strain zone. Just a different representation of the value. So at the end, in Sardinia, we can recognize a situation like this. We have approaching from the south to the shear zone. We have a lot of faults to the south due to the same deformation. There we can see an example of this kind of fold in paragnosis, albeit bearing paragnosis, with an axial plane indicated divergence to the north. And these folds became tight and are transposed completely approaching the shear zone, where we are in starolite zone, kyanite zone, or sillimanite and white mica zone. Here deformation is very, very strong, and we have a very well development of mylonitic rocks and the mica schist and the orthognesis. Sorry. So you have folds here and shearing here, but the shearing is by simple shear, dextral simple shear, vertical foliation, so horizontal lineation, and a component of transpression like this. This component of compression is the one responsible of the fold, because we have also a dating not yet published. We dated also the foliation of these folds by monazite growing along the foliation, and the age is exactly the same as the age of shearing. So these two structure, the folds and the shearing, are contemporaneous. It is a different um, repartition of the deformation. Here, the pure shear is accommodated by folding. Here, since simple shear increases, the formation is accommodated by development of myelonitic rocks and the strong shearing, as you can see in the picture and so on. This has been observed not only in northeastern Sardinia, but also in the north central part, in the northwestern part. So we had several data because we worked in this part of Sardinia for several years. So with several theses, master theses, several PhD students. So the situation is quite well constrained. Okay, if we put together this information, there are also the first paper pointing at expression was this one with a colleague from Siena University, a petrologist. It is not 22, but 2000, no, not 3 years ago, but 20 and more years ago. We pointed out the occurrence of transpression and exhumation during D2. So this is more or less the schematic representation of the PT path of the rocks with the ages, collision, D2 transpression, and the final part, D3. Because also in the shear zone, we observed by quartz analysis also some mechanism of deformation with decreasing temperature, or also mineral, maybe chlorite after biotite. So the shear zone started in amphibolite facies, but ended in green schist facies of metamorphism. And the deformation is more or less here. To block, moving in a dextral way and pushing each other. So you have a vertical extrusion, a movement of a particle. If you move this block one towards the other, one point here, follow this trajectory and move upward. In this case, we made some models with Jacopini, Pasquier, and Daniel Ken, because if you have a lot of pure shear, vertical pure shear, you needed to have a vertical lineation, not an horizontal lineation. So it was tricky because we observed exhumation of rocks, because during D2, rocks moved from 9 kilobar to 4, 5 kilobar. So several kilobar of exhumation means 10, 15 kilometers. But we had the lineation more or less shallow dipping, not vertical. It was tricky, and we tried to make some numerical models with Daniel Ken, and we demonstrated more or less that also with the subhorizontal lineation, you can have also an important component of your shear, because it depends, the orientation relation is in between the simple shear, one-end member, and pure shear from horizontal to vertical, but it depends also on the amount of strain, not only vorticity, but of strain, also on the time of application. But in this model, we are able to demonstrate by numerical models that it was possible to generate subhorizontal lineation with a vertical extrusion. This problem has been faced by Tico, Fefos in the 90s. So there are beautiful paper showing the switching of lineation from horizontal to vertical and so on. But at the end, we can explain the exhumation of rock. Okay, of course, we can put numerical data, depth, timing of deformation, maybe 20 million years, starting from 12 kilobars, maybe 50 and more kilometers. So just with numerical model, we are able to explain this kind of observation. So D2 deformation is due to transpression, and transpression caused the exhumation of these rocks. Okay, just to have a quick summary of this. Going to the large scale, So we gained the ages. Most of what I've shown you here came from this part of Sardinia, but we have data, the same data also here and here by vorticity. We have also some other methods of vorticity and geochronology. And in this part, we have also some all the data about white micas, because in the paper by De Vincenzo and others, 2004, I have not put the picture, but we applied more than 20 years ago laser ablation to gain the data on the albite porphyroblasts. We have albite porphyroblasts surrounded by the S2 foliation, the mica schist is albite, and within albite we have garnet, biotite, large flake muscovite, ilmenite, quartz, and so on. That is a older S1 foliation. There are also white mica, of course, along the S2 foliation, maybe also something in the strange shadow. So we, by laser ablation, we dated this large mica for argon analysis, and we found inside the albite porphyroblast ages of 340, 330 million years. Okay, that was more or less related to the S1 deformation, D1, and collision. In the external part, we found a large crystal of mica with the core with 330 million years, and the rim of mica, of the white mica, maybe 320, 315 million years. So big micas were not completely equilibrated during the two deformation, during the compression or exhumation. And we had a lot of these ages. Of course, this means that this mica has been rotated into parallelism with S2 foliation and partly re-equilibrated. Some white micas have started as a new crystal along the foliation, showing ages of 300 million years in the core, in the rim, and so on. But it was the first datings of deformation, both collisional deformation and the D2 deformation in Sardinia after 30 years after the first try of datings of the age of rock. Here we are in the southeastern France. The East Variscan shear zone has a different name, Cavalier fault, but it's not it's not a problem. This stuff is made of migmatites. This is a boarding shear zone, a dextral one. These are amphibolite facies metamorphism, low-grade metamorphism. And also Matteo Simonetti, during the PhD thesis, studied also the Aiguirus Massif, another massif in the Western Alps, with the same similar situation with respect to Argentera. This kind of shearing, industrial shearing, with the same age, the same vorticity, the same attitude of foliation, but these shear zones are inside the migmatite. These one are at the boundary between migmatite and medium grade metamorphic rocks. So they are expression of the same kinematic and deformation, but in different, slightly different place. Of course, we have different starting timing of the shearing. In the Argentera 340, here 320, here 323, 320 more or less in the Posada in Sardinia strand, because we made the same work also in the more massif. The rocks are absolutely the same. You can say the same rocks here, 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 and here. No problem. That's beautiful minerals and beautiful deformation, and also beautiful sea. Okay, so we think about not a single shear zone, but a wide piece of lithosphere affected by an anastomosing well network of shear zone. So not one, but different shear zone connecting with activation in different times. Okay, so we concentrated more in this part of Sardinia or Estuariscan shear zone. In the napped zone of Sardinia, where there are a lot of tectonic units, there is a small mountain in the central part that is called Mount Grigini, a strange name, but it's very important because it has sheared leucogranites, staurolite-bearing mica schist with garnet, and the low-grade rocks, medium-grade rocks, and a shear zone inside. This complex has been interpreted up to 2 or 3 years ago as a core complex, following the models by Malaviel and the Montagne Noire and some other papers. But what we can observe is the attitude of the foliation. No, the attitude of the foliation is nearly vertical. Uh, is or vertical, nearly vertical, and is not flat. Because if you have a core complex, like the one I showed before, the magnetic foliation is wrapping around the core complex antiform, so it is very flat in the upper part. Here we have a vertical foliation everywhere, and the stretching lineation, elongation lineation, is more or less subhorizontal, or slightly dipping to the southeast. So just this thing is strange, and we we study again this small massive to detect the occurrence of maybe transspecial deformation as in the northern part. So with the PhD students, we made a new mapping of the high shear zone. We collected several samples. Uh, is more or less geological section. You can see orthognesis and mica schist with large folds that became tight and tight towards the shear zone. These red are intrusive complex, are leucogrants intruded and sheared in the shear zone. There are some aspects of the foliation, vertical foliation and subhorizontal tenuation in the picture. Uh, nice shearing the mica schist. So it's a very beautiful example of shear zone. Very nice to observe in the field. You can see also the poles of the foliation. The pole of foliation are here, means the foliation is this one, so nearly vertical or highly dipping. The lineation is in this position. The axis of this fold are more or less parallel to the lineation. Also, the later fold axes are parallel, and these are axes related to a late stage of folding with open fold and so horizontal acceleration, but very open fold, so they not destroy very much the original situation. Do you know this picture very well because I showed you before? Is a leucogranite SC structure in the sample, beautiful mica fish in section, dextral sensor shear by SCC prime structure. This is the same. So for the sense of shear, no problem. The age of this granite is around 310, 320 million years. Up to few years ago, there was attributed to the latest stage of the Variscan origin, maybe 300 or 290 by a very old datation, maybe 40 years ago, but never published. But this granite included more or less in this time span and has been affected by shearing, ductile shearing. So here you can see some some picture. You recognize some deformation of quartz here. What do you see here? Do you remember the formation mechanism? You can see the boundary are amoeboid. So you are in the deeper structure, grain boundary migration, because you are also in metamorphic condition with garnet, sterolite, so a very hot deformation around the 600 degrees and so on. You have mica fish, feldspar, porphyroclast, kinematic indicators. So we had also some estimation of the vorticity, and we have more or less this kind of vorticity with amount of pure shear 77%. So pure shear dominated the flow. Okay, we had the datings by monazite, the same methods. Not very beautiful monazite for zoning, but useful for to detect the edge of shearing that more or less is in agreement with the shearing of the northern part. And with Pier Lanari in Berna, we analyzed also chemical map of the micas to detect more or less the condition of metamorphism, quite complex method, but we had a large estimation of the deformation, but you can see deformation like this, 600, 680, and the pressure in this span here. Mm. But again, I cannot go through this complex methodology. More or less, the best sample that we dated returned age of 321 million years and 311 million years. Is a good concordance in age. So this is more or less the age of the shearing. We can also check the different domain of the monazite with the amount of lighter rare earth element and heavy rare earth element. So, for example, in the core of the garnet, there is low amount of HRS and increase in the rim of the garnet. So there is a correlation in between structural position, ages, and amount of yttrium or rare earth element. So this is a good control when we try to interpret the age by dating monazite. So what happened in this old picture? We can you can say what's happening in Sardinia or more or less in the south of Riscambert up to France or Western Alps during the late Carboniferous. There is, of course, the collision after the consumption of the oceanic lithosphere. There is a collision with the occurrence of migmatite complex here. This Variscan shear zone that operated initially as a thrust, that thrust. There are evidence in some places. I didn't spoke about this. And at this time, we have the collision and the thickening stage with D1 deformation, Barovian metamorphism, strong deformation here, just start the exhumation of the migmatites here, and the deformation is moving towards the foreland. Okay. After a few million years, 320, 300 million years, the formation affected the foreland. D2 deformation caused back folding and back shearing, giving rise to the development of the S-Variscan shear zone, but also in the NAP zone, this regional antiform was deformed by the dextral shear in the Mount Grigini. So we have more or less dextral shear here, dextral shear here. Here is a little bit younger with respect to this one, but it is not strange because deformation is moving to the south. So first started in this part and then moved in this one. But more or less all over the Variscan belt, we have strike slip or transpressional deformation here, here, and also some in some tectonic contacts. I come back to Sardinia. Okay. Also along some of the tectonic contacts that are quite brittle, thrust, sometimes you can observe subhorizontal uh, lineation. Means that after thrusting, there is a little bit shearing in this direction. So it is not so uncommon, but a little bit not well developed in the interpretations. Okay, so the final picture is that this part, this orocline, this small orocline, is affected in this part by a huge transpression of a risk and deformation, 330, 300 million years, with an astomosing shape, because you have a shear zone in the migmatites here, and shear zone at the boundary between the high-grade metamorphic complex and the medium-grade metamorphic complex here. And the deformation also affected the external part of the belt. The shear zone in Mount Grigny is a good example. And also the thrust reworked as a strike slip shear zone are useful example also in the brittle part of the Variscan belt. So it is the example of a huge shear zone that we can study by structural geology. Mapping, of course, is the first thing that we need to do to understand the geometry of the rock bodies. Uh, the the geometry of the shear zone, the kinematic is very well important. We detected also the metamorphic path of the rock by petrology or by thermobarometry with different methods. We try to gain the information of the age to be sure that it's the same shearing by petrochronology using monazite. It's very useful chronometer because we can, especially by laser ablation, because we can we can gain advantage of the position, structural position of the minerals. It is very, very important. We did the same in the Himalayas. And also we gained information about the flow during the formation, the vorticity. It is not a precise method, it's just an idea, but with different approach, we more or less we found all along several transects the occurrence of pure shear deformation accompanied simple shear deformation. This is very important because this kind of flow could explain the exhumation happened during the to deformation, the axial shearing. So there are several things that combine in a possible interpretation. I am not sure this is the best one or the final one. Maybe in 10 years people found some other things, some other findings, probably, and surely, because in the history we observed things like this. But up to now, we try to combine all the possible information with modern technique to have a good interpretation. It is not the final one, but it is the best one at this moment. Maybe tomorrow I will change idea, but if you have several methods, several observation, a concordant observation, it is better because you can build up a more solid interpretation. Okay, with just the taking home message from this morning before lunch. It's time to stop. Okay, we can stop a little bit before. This is a landscape from Sardinia. This is a Variscan basement. These are Jurassic Cretaceous limestone, just not deformed. This nice place will host the Einstein telescope. It is the infrastructure that is made by a triangle with tanks uh, each side, put at 300 meters below the surface. So very big work. So our study were important to characterize the geology of the area because you have to uh, you have tunnels for 10 kilometers so with a large, maybe 8 meters, and at the corner of the triangle you have a big space, maybe with the altitude of 30 meters and 200 meters in horizontal position. So the stability of the rocks is very important. But this is a very nice place because there is no deformation. By satellite, you cannot see much more vertical movement of the rocks or horizontal movement. So it is one of the best place to host this kind of telescope because they should catch uh, very small, very tiny signals. So they need to have a laser running in the triangle at nearly at zero temperature, absolute zero temperature, with a void and with no noise to be able to catch the teeny signals of astronomy. So, okay, just anyway, it is a nice place that probably will be little bit disturbed by this by the work of this telescope for a few years. But the telescope will be underground, so after a few years, the situation will come back in a quite place. Okay, have you some question about this big overview of the Variscan shear zone? Okay, okay, thank you, and enjoy the lunch. I have not understand if this afternoon we can come back to the geological department to see some thin section of porphyroblast infoliation. Yes? Okay. You will say yes. Okay. Uh, by using the software of Volkmar Polmer, We can gain information about the long axis, the short axis, the centroid of each strain marker, and then we can use for earthy uh, analysis or fry analysis, so we can use a different approach for finite strain. It's very nice. Okay. Have you your computer with you or? Okay. Uh, so, okay. If you have, bring it so you can do by yourself. I will show you how to do, and you can try. Okay. Okay. To download. Oh, it's very easy to download. Very quick. So is Ellipse Fit the name? Is, Ellipse Fit. You by Google you can search and download that. If there is a free download for Macintosh or other computer, no problem. But we can download after lunch, no problem. We have time. Thank you very much. You think we can start? Okay. Okay, good afternoon. Now we will speak about finite train with some practical exercise. Okay, as you know about the deformation, strain is quite heterogeneous. We have observed this heterogeneity in crustal scaly shear zone. For example, the horizontal shear zone has a deformation concentrated in a high strain shear zone to the north in Variscan Belt in Sardinia. To the south, the deformation is characterized by folds. So usually deformation at the natural scale is heterogeneous, but it is always possible to find a small volume of rock where deformation could be regarded as homogeneous. That means that every point in this small volume has been characterized by exactly the same amount of strain. So even in a fold, we are in a fold, more or less, you can find a small piece of the fold in the limb or in the hinge, where the formation could be regarded as homogeneous. In this way, we can apply finite strain. We can try to quantify the amount of deformation suffered by the rocks. As you know, deformation could be continuous or discontinuous. Discontinuous deformation give rise to fault, break, discontinuity in the rock mass, whereas continuous deformation is very interesting because in this case we can apply our methods of finite strain. So small homogeneous volume and continuous deformation with no break. Okay, just we recall some basic feature of deformation. Uh, you know that we can have a change in length of line. We observed Boudin. Here is a nice example of Boudin in Greece by Paris Xipolias. Some more competent layers has been broken into pieces, and each pieces is standard with respect to the other. In a situation like this, we can take a quantitative measurement of strain by summing up the length of these bodies, L1, L2, L3, L4. So we sum up and we have the initial length of the line before stretching. And from this point to the other one, including the Boudin and the space between one Boudin and the other, we have the final length of this line. So we can calculate extension by il L final L minus initial length divided initial length. In this way, we can calculate the extension suffered by this line. If we are in the case of extension, E is positive. If we are in contraction, in shortening, you are measuring the deformation along a fold, E is below zero, is negative, because you have contraction. The final length is less than the initial length. This is a case of folds, also from Greece. You have folds like this, then you can uh, measure the length of this red line, that is the initial line, and this is the final length. The final length is less than the initial one, so your calculation give a negative extension, contraction. There are other ways to represent linear deformation. It is lambda, is 1 plus e elevated this exponent, and also the stretching is 1 plus e, just different way to represent elongation of lines. As you know, there is also the shear strain that is just the tangent of the angle in between this straight line and the distorted line by simple shear. This angle, the tangent is just the amount of simple shear. that is related to amount of displacement during deformation. We saw in the last days this kind of deformation. As a change in angles, there are some beautiful examples from the Moyne Trust zone in Scotland, because this is a trust connected to the Moyne Trust. Let me show you the lesson before. Below there are quartzite or pipe rocks of 150 million years. Pipe rocks means that you have this kind of burrows that are distorted by the strain, because we have a strain like this. So these burrows are no longer perpendicular to the backdin, but that has been distorted by simple shear. So you can simply take a measurement of this angle and gain the information about the shear strain just in the field with pipe rocks, with warm burrows happened in the Cambrian and then deformed a little bit after. Of course, also in the shear zone, this is one of the shear zones that I show you from Capo de Creus in northeastern Spain. You have an older foliation deflected into parallelism with a shear zone. You can take an estimation of the shear strain by the deflection of this foliation that progressively became parallel to the shear zone. There's another possibility to apply shear strain. Okay, this just the variation in shear strain at small scale. You can take a measurement of shear strain along a different section, and you can gain different values, because the formation is heterogeneous not only in this direction, but also in the direction of shearing, as we saw from the example by Fossen Cavalcante of the shear zone in the Adamello region. Just it is not in a normal situation, but is normal to find this kind of things. Okay, now we recall a little bit about the strain ellipse. After you have undeformed state represented by a circle, after homogeneous deformation and continuous deformation, this circle became an ellipse with a long axis and a short axis. So the fine strain means to characterize the shape of the ellipse in the deformed state. Of course, changing from a circle to an elliptic shape, this part has been shortened. This part has been lengthened, the red one, to gain this final shape. This is just okay. And when we deal with the deformation, we have obviously all the lines are shortened or elongated, and change the angles with respect to the main axis of the finite strain. Only two axes remain perpendicular, the short axis and the longest axis, Z and X, that are called the principal axis of strain. They are quite important because in three dimension they help us to recognize the foliation in the rock and the x epsilon plane in the deformed rocks. So usually in two dimension we use the ratio from the length of the longest axis x and the length of the short axis, this one. So this divided by this one. This characterize axial ratio characterizes the shape of a ellipse. Okay, in two dimension. Okay, no more important. Okay, so when we try to apply this kind of method to deformed rocks, here we have a good example of a Triassic rocks deformed in the Northern Apennine. We have cluster of marble, of quartzite, and you can see that these clusters are elongated in this direction and shortened in this direction, maybe along the main foliation. Um, and why we we use ellipse to take information of strain? Because many rock element, mineral, cluster, display an elliptical shape after deformation, or a shape very close to an elliptical one. So in this case, they are not true elliptic. You can see a shape like this, very irregular or rectangular, but you can fit an ellipsoidal shape inside this object. So you can approximate this object to an elliptical shape. And of course, you cannot use only one cluster of this deformed breccia, this metabreccia, but we have to use many clusters, maybe 40, 50, to have a good indication of strain. Here there is a problem because the cluster have different composition, um, marble cluster and the quartz cluster. You can see the marble cluster are very strongly flattened and shortened. Quartz cluster remain more or less rectangular or more or less spherical in shape. So there is a big difference in contrast in rheology between this one and this one. So if you use marble cluster, you can have value of strain that is quite different from this one that underrepresent the strain undergone by the rock, because it is too strong. Is well deformable, so more or less mark the deformation history and all the strains underwent by the rock. This one is not good. Anyway, just in a theoretical way, if you take information by this kind of cluster, you can estimate the different rheology, different viscosity at the time of deformation. Okay, finite strain is useful for the study of fold kinematics. If you put strain ellipses on the fold hinge limbs, you can detect a different mechanism of deformation. They has been used by to detect deformation mechanism, to detect the origin and significance of a planar anisotropies. So the first study is to detect that the x epsilon plane of the finite strain ellipsoid has been made by finite strain analysis of over 100 of sample. They are useful if you try to build up balanced cross-section in the innermost part of the genic belt, because in the outer part, where you have a thrust and fold related to thrust, you can simply retrodeform the section by linear deformation. But if there is a strain inside the bedding, you have also to calculate strain and to destrain the bedding before make this kind of retro deformation to have a good value of shortening or representation of the initial situation. So every time you have an internal deformation in your bedding, deformed rocks, deformed conglomerates, deformed breccias, you have to calculate strain and to detract strain from the retro deformation. The finite strain has been used to calculate the deformation and to show the variation of deformation around the plutonic rocks, around the granites, to try to understand the way in which they intrude the country rock. They has been used for quantitative analysis of simple shear and pull shear component and the volume changes. Uh, because there is another important thing that I forgot to tell you. Do you remember a square like this, deformed by pure shear, simple shear? You have a situation like this, distortion. Okay, some people is able to quantify this kind of extrusion from this part to this part because we have vorticity in between 0 and 1, simple shear and pure shear. But if you add finite strain of the deformed object, so finite strain plus vorticity, you can estimate the amount of extrusion of this ductile shear zone, of this non-coaxial shear zone. And this work has been done by Riclot in the South Tibetan detachment, or other people, Himalayas in some uh, deformation in Greece. So adding finite deformation to vorticity, you can estimate the amount of extrusion that the rock underwent during no coaxial deformation. So it's a very important finding. Okay. Okay, in this paper, maybe Law and others, 2002, this has been applied to the South Tibetan detachment. Okay. And also, uh, Matteo Simonetti used this method to calculate the extrusion in the Argentera shear zone, adding vorticity values to finite strain values. Okay, to calculate a strain ellipse, we need good strain markers. What is a strain marker? A strain marker is an object that is present in rock before deformation and has been deformed homogeneously and continuously without breaking, without recrystallization, just changing the shape, shortening and elongating according to the overall strain ellipse working in this rock. So, for example, there's metaphyllites or metaconglomerates, maybe from Greece, in these kind of rocks. Paris Tripolias was able to calculate strain using a lot of these strain marker because there are no fracture. You can see under the microscope there is no recrystallization, no bulging, no grand boundary migration, no other mechanism, no ondulous extinction. So they just change the shape without fracturing or recrystallizing. So these are good strain marker, and they can use this kind of marker to calculate strain. These are deformed breccias. Also, the class of the breccia are very good strain marker. This axial ratio calculated is 6.72. In this section, the ratio is much more than 7. But also these objects are very useful. Of course, they are big objects. You cannot use the scene section, just a picture in the field, because in scene section you can see only a fragment of the class, of course. Okay, this is a good deformed rock for strain analysis, but not this, because in this scene section you can see that the quartz has been recrystallized, so the original crystal has been lost, and then you can see uh, mobile grain boundaries like this, ondulous extinction, and so this kind of quartzite is not good calculated strain. So you can do nothing with finite strain, or you can calculate strain. You can try measuring this long axis, short axis, but we have a minimal estimate of strain, and just in a small moment of all the deformation history. So you can do more or less nothing with with this data. With this rock, with good strain marker, you can go ahead and calculate the strain. Uh, you can, the first years, the strain was calculated by fossils, using fossils, with the trilobite distorted by shortening in this direction, elongation in this direction, shear strain here, because they have a strong symmetry, and so you can also calculate the gamma value. But the problem of the fossils is that they are on the bedding surface, not in other place, in other surfaces. So you cannot take advantage of the 3D dimension. Instead, reduction spot oxidizes iron and reduced iron make this kind of elliptical shape. They are perfect to calculate strain. They are in the volume of the rock, so you can use this to calculate strain. Okay. When you have a good strain marker, you can try to use some of the available methods to calculate strain. If you, for example, you have some oolite in a rock, is before the formation, undeformed state represented by a circle. You have this circular shape of the oolite, perfect. The distance between one center and the other is more or less constant. So this length L is more or less constant from this one and the closest, the nearest neighbor. After deformation, you can observe the change of the shape of the circle that became elliptical, and also this line changes the length. This line is elongated, and the new length is L1. This one is shortened because it's close to the shortening direction, and so on. After, of course, this kind of line rotate also into parallelism with the x-axis of the finite strain. So what we can see after pure shear or simple shear or mix of the two is the change of the shape of the object from circular to elliptic, a change in the length of line, a change in the angle that this line make with the mm, principal axis of the strain ellipsis, and also there is a change in the position of the centroid of this object, because in this direction they are shortened. So these two objects, they shorten their distance like this. In this direction, the objects are elongated like this. And the maximum elongation of the distance is in this direction. The maximum shortening is in this direction. So uh, just looking at this simple picture, you can use a different approach. You can use the change in shape from circular to elliptic, the change in length, the change in the angle between the lines, and also the change in the position of the centroid of the strain marker. The last method is the so-called Fry method that uses the position of the centroid to detect the finite strain. The other method are the RFI method, mm, using the axial ratio of one object, long axis, short axis, and orientation of the long axis. It is very useful, this method. And there are also other methods, but little bit complicated, because if you measure the length of these lines, you can have you take a measurement in the surface. You have a situation like this. This was used by Ramsey several years ago. You can have this, the length of a line in centimeter, and this more or less the angle. So more or less you have a sinusoidal shape of the line. So the longest line arrive at this point, the shortest line at this point. So if you make a ratio between this point and this one, more or less you can calculate the finite strain. But it is very long because every segment should be measured with a relative angle, so you need a lot of time. But more or less, you can gain information also by the length of the lines. But this method has been overcome by Fry because he used the centroid of the object that are more or less connected to the length of the distance between the different objects in a very easy way, much more easy way. Okay, the strain analysis by RFE method is quite easy, not so easy to do manually because you need to take a lot of information. More or less, we need to estimate the long axis, the short axis, to have the ratio, and the angle between the long axis and a main direction. In this picture, you can see undeformed state with object with the same axial ratio, initial axial ratio equal to 2, and the different orientation of the ellipses 1, 2, 3, 4, 5, 6, 7. If a plot in a graph where you can put here the axial ratio and the orientation from 0 to 90, from 0 to minus 90, you start from this position because all these objects have an axial ratio equal to 2, so you have to project all the ellipses in this line, okay, undeformed state. If you start to deform it by homogeneous deformation, you have contraction here, extension here. What you observe is a change of the shape of this elliptical object. They rotate a little bit, and their distribution, when you take measurement of long axis, short axis orientation, the distribution is no longer along a line, but they go in a curve like this. Because, for example, if I take this object is vertical, but vertical is also the shortening. So this object became shortened, and when you reach a deformation similar to 2, it became spherical. Okay? So this is the minor axial ratio that you can measure on the graph. The opposite happened to this kind of class because it is oriented parallel to the long axis, so it is shortened, elongated much more. So again, the much higher axial ratio here, the number 7, the number 1 is here. All the other objects are in this position between the highest and the less deformed object in this distribution. If the strain, axial ratio of the strain is 1.2, that is minor than initial axial ratio of the object, the distribution is from 90 to minus 90. All of the orientation are more or less preserved. If you increase the strain, and the strain ellipse has axial ratio equal to 3, 3 is more than 2, uh, of course, this reasoning go ahead. This object became spherical, and after that became flattened in this direction, elongated in this direction. But it is a less deformed object in the group, and this is in this position. The ellipse 7 continue to be stretched in this direction and short in this one. So the axial ratio is the maximum and is this point in this situation. And the other are in a closed shape, in a curve with a closed shape like this. So more or less, when you project your data on RF phi angle, phi is the angle that I measure here. If you have a dispersion from 90 to minus 90, means that the deformation is less than the initial axial ratio. When the point are distributed in this way in a closed curve, means that the strain is higher than the initial axial ratio. Okay. This is an example by Tripolias, just mm, on this kind of deformed quartzite. So they used this class as a strain marker. I projected on a LC graph, just rotated in this way. You can see that, of course, the cluster not along one line, but occupy different line because you have different initial aspect ratio. It is not equal to 2 as in the case before, but you have a different initial aspect ratio, so they occupy a closed area like this. Okay. Okay, this method was developed by Ramsey, then was used also by Dunnett in the 80s. Then Richard Lyle, applied also different object, different lines, because these are lines of initial uh, axial ratio, of the same axial ratio. This one, there are other one. And also he used the theta lines that are the loci of the object that have the same orientation. So other line in this way, uh, over each line there is an object with the same initial orientation. So he made an improvement in this method because at the beginning people use the manually and they try to fit the point above the line that has been constructed by former computer. So it was a manual fit and it was not easy. But with the theta line, it was much more easy to fit and to try to find the final result. Okay, I assume that more or less you know this method. Uh, there are also variation using tensor calculation because you can put the axial ratio and the orientation in a two-dimensional matrix of deformation. There was a method by Shimamoto and Ikeda, I don't remember 19 something. It was a numerical method. And more or less, if you use the arithmetic mean of the RF and the arithmetic mean of the orientation, you can have just an estimate of the finite strain. Okay. Otherwise, you can use some pre-prepared graph by Lyle. There is a book with different graph constructed by for different RF and different strain applied. You have to project your data and to put above this graph to try to find the best fit. Okay. So it is very time-consuming method because you need to have at least 50 objects in a section. 50 objects means 150 measurement of axis and orientation. Then you project on a tracing paper for one section, then you put above the pre-constituted graph and try to find the best fit just for one section, but you need in three dimension at least two sections, so you need to make 300 and more measurements. It's very time consuming. But now with the software developed by Volmer, it is much more easy because you can just try to obtain the data of the axis and the centroid orientation, and then they apply the method for frame method, RC, and so on. Okay. And of course, if you use this method of finite strain, it is based on the changing in shape of this object, but you are not sure that this object is deforming in the same way as a matrix. should be a difference in competence contrast. Mm. Competence contrast is visible because maybe the foliation is wrapped around this cluster. So maybe this method underestimated the real strain a little bit. Mm. So, for example, Norman Fry, an English geologist, uh, uses this kind of change of the lines in between a packed fully packed object of around maybe lights, because in the form of the state these lines are more or less of the same length. After deformation, these lines are deformed according to the strain ellipse. So you can take a single measurement of this line, this line, this line, and project in a graph like this, like the one I put there, or he developed a simple method, a graphical method that is quite easy, because you have to take a picture. You have a tracing paper. You put the center of tracing paper here. You put the tracing paper above this, or better, you can put above and mark the position of the center like this. Then you can take a second tracing paper, this one, two. You put above this is your center, the center two, you put on this position, and you mark the position of the center around. You shift to this point and mark the position of the point around, and so on. Maybe it is better to to put number to avoid to repeat the same thing on the same point. And after at least 50 displacement of the tracing paper, you have to take care not to rotate the tracing paper. You have to translate parallel to the axis with no rotation. If you do this after 50 displacement, you can show a distribution of a point with a high density cloud here with low density point in the central part. This is just the strain ellipsoid. It's proportional to the strain ellipsoid. So if you take the long axis and the short axis, make the axial ratio is the axial ratio of the strain ellipsoid. It is the same as go to take consideration this one, this one, this one, and make a long calculation is exactly the same, because the principle is the same, but he was able to find this very quick method, because if you have in section or a picture, you can apply in a few minutes, maybe half an hour, listening music, maybe so. Because not it is not so difficult, no? Just to repeat the point, you can watch television, maybe. So it was very popular, this method, and moreover, it it will take into consideration the position of the cluster, but not the shape. So you can have also a strong difference in contrast, in competence contrast between the matrix and the object, but the object changes the position in the space, so you record the strain in a good way. Okay, be careful, because prime method can be used. Okay, also on rocks that have a pressure solution along grain boundaries. If the grain is not dissolved completely, you can use at the same time, but you take care. Okay, and usually is applied to sand grain in sandstone, voids in limestone, pebbles in conglomerate, but you can use also in feldspar, maybe in deformed rocks, but usually is applied in this condition. Okay, of course, using the Volmer program, you maybe you can mm, visualize the perimeter of the object and calculate the major axis, minor axis, and the position of the center. Then the output could be RP method, Fry method, without do much more calculation. Okay, but what we need is to calculate the strain in 3 dimension. So the best way is to use the principal plane of the finite strain ellipsoid. A strain ellipsoid is made by long axis, intermediate axis, and shorter axis, A1, A2, A3, or X, epsilon, Z. But if you use two of these plane, you are able to calculate strain. If you use other section, you must calculate strain in a very different, very complex way, because you have to do a long calculation to gain information of the principal plane. So the best thing is to use the principal plane of the finite strain ellipsoid. Maybe the xz and the x epsilon, that is the foliation of the rock, is the lineation. So when you go in the field and you take your oriented sample, so you are in the field, you have a lot of rock, you have a foliation like this in the rock, you you mark the orientation, the strike of this surface, marking the direction of the north, the dipping, maybe north 120, 55 degrees toward the southwest. This is orientation, and you mark on the sample. Then you broke the sample by with the hammer. Usually it breaks just when you put the orientation. You took away the sample, then you go in the laboratory, and you will try, of course, to break the sample along the foliation, because it is a very easy plane to break rocks. And if you have the foliation like this, maybe you have conglomerates. So the foliation is this plane of the strain ellipsoid, one of the principal plane. On this plane, you can observe the elongation of the object or the growth of mineral in a preferred orientation. So this is the maximum axis of the strain. So you need to cut this rock in 2 sections, at least 2 sections. One should be the foliation, if it is enough good. The other one is perpendicular to the foliation and parallel to the lineation, where you can see the maximum deformation, and it is a xz plane. So with two plane, you are able to calculate the third one. So you characterize completely the finite strain ellipsoid. Otherwise, if the foliation is not good, you can cut the sample uh, not parallel to the lineation, but perpendicular to the lineation in this way. And you have the third section of the finite strain ellipsoid, that usually show less deformation because you have a maximum shortening and intermediate axis. The maximum deformation is visible on this section, XZ. Maximum elongation, maximum shortening, so maximum deformation. Because if you have, for example, the axial ratio on this plane and the axial ratio on this plane, you need to calculate the axial ratio on this plane. So So you just divide this axial ratio by this one, and you obtain okay, is opposite. No, you have this one, sorry, XZ, okay, okay, this is exception. So you divide these two ratio and you obtain the epsilon z axial ratio, just to have the deformation of the three plane main surface of the finite strain ellipsoid. Just it is quite simple. Okay, so when you have a deformed sample, you must cut along two of the three main principal plane of a strain ellipsoid. Because if you have a cut oblique to the to the principal plane, maybe you you cut in this direction, you have a component, and then you need at least three different cut or more, and you need to calculate by matrix deformation the principal strain, but it is quite complex. There is a paper by Owens at the end of the 80s with all the calculation. During the PhD, I tried to write a program to calculate this one. It was very complex because you need at least three or four surfaces. You have much more surfaces better. So a lot of work, especially at that time that I worked manually. So several months of work. So the best thing is to have one of these, two of these three principal planes. Then the work is much more easy. Okay. Okay, this is a sample from Sardinia. There are Cambrian breccias uh, formed along a fault escarpment during the extension of the Cambrian continent, the southern Cambrian continent. And this breccia, carbonatic breccia made of limestone, more or less, are deformed, are strongly deformed. And I took a sample. The sample is cut along the XZ section, where you can see a strong elongation and a strong shortening perpendicular. Is a good section. The other one is a perpendicular section, and you can see that there is a small elongation, not so strong like this. So you can also infer the kind of ellipsoid, because if you had elongation in this surface, you are more or less z epsilon elongate x elongate, so you are in pancake ellipsoid, more or less. If in this section you observe circular object, probably you are in a Sega shape ellipsoid. So you can have just qualitative estimation of the strain ellipsoid. Okay. So usually, if you give a look to this section, you can more or less assess if you are in general constriction or in general flattening or axial flattening. So of course, you have to calculate exactly the acceleration to project on the Flynn graph, but you can have an idea of this one. So in this kind of object, a prolate result, in a section like this, you can observe circular shape. In this one, you can observe elongated shape everywhere because it is like a pizza. You cut a pizza in every direction, and you can see everywhere the elongation of the object. Okay, when you use finite strain, usually you project your data on the Flynn graph, so you can find the coordinate of the point here, and you can assess the kind of ellipsoid. But keep in mind that this line is where K is 1, is for mm, condition of deformation with no change in volume. If the volume decreases, this line shifts to the right. If the volume increases, this line shifts to the upper part. But if the volume is in between, the less of the gain volume is in between minus 20 or plus 20%, more or less, this line is a good approximation. So you have to check also to have not so much loss or gain of volume in the rock. Okay. Of course, the kind of deformation, the kind of strain ellipsoid uh, make different kind of rock because in this part, in the pizza shape or pancake ellipsoid, you have mainly foliation but not alienation. You cannot find delineation here because a pizza is round and every direction is the same. So you cannot assess the occurrence of, of elongation lineation above. So this is S tectonite. S means schistosity, foliation. This you can start to have a lineation on the foliation. In this field, there is a better situation. You have a good foliation, a very good lineation, so you can verify very well the principal plane of the strain. Here you can have less foliation and much more developed delineation up to cigar shape ellipsoid where you have only lineation and no foliation. So in the field you sometimes it is difficult to find the foliation or to find the lineation because you should be magari in this position or in this other condition. So it depends also on the kind of deformation. Okay, just an example. Okay, we can go ahead. In this picture, it is represented more or less the field of flattening. You can see more or less little bit stretch inclination here, but not so strong. And XZ and epsilon Z section are more or less similar, not much difference. You have much more difference in the plane strain, so there is a good delineation, is much more strong deformation, less deformation. In this part, you have a stretch inclination, strong deformation here, and no deformation in this phase. Okay, no problem. Oh, this is just an information. You can see the filling graph and this kind of strange plot. Do you know what are they? Oh, you can see here indirect evaluation of 3D strain by quartz C fabric. Okay, there are methods to take measurement of quartz C fabric, quartz C axis under the microscope. You can use a universal stage. You can take a crystal of quartz, so you rotate until the C axis is vertical, so it completely in extinction. And to do this, you need maybe 4 or 5 days for one section because you need 400 of C-axis, and then you project all the observed C-axis on a stereographic projection, and they try to build up this kind of skeleton. So that is the distribution of C-axis is not uniform, but just follow this geometry that is controlled by the shape of the finite strain. So if you have a distribution of C-axis like this, you are in plane strain. If you have a distribution of this like this, you are in apparent flattening, or this apparent constriction. And this is for the C-axis of the quartz, the main axis. This is for the basal prism, another axis. This is also important because by measuring C-axis, you can also have an estimation of the vorticity of the flow. So, but to do this manually is very long. It is better to put this insection under electronic microscope with electron backscattered machine that collect in few hours all the information about the z-axis, the magnitude of the grain size, so complete information. It is quite expensive, but it's very useful. Anyway, using the z-axis, of course, we have also an idea, an estimation of the 3D strain. It is an independent method. Okay, Xipolias worked a lot on this. These are some graph of the quartz z-axis. Of course, you have contouring, you have maybe 400, 500 measurements, so you have to do some statistic of this graph. And by the position of the maxima, you can try to draw this kind um, of a skeleton. For example, this one is related to related ellipsoid, this one to pancake ellipsoid, this one more or less to plane strain, but you can see that here there is a symmetry of this axis and this one. Here the symmetry is lost, there is a rotation, and it is due to simple shear. So by using the z-axis, you can also assess the sense of shear in the rock. It is very useful. Uh, U means universal stage, means that he spent several weeks measuring a single axis, because when you have scene section, you have to move along three different angles to make the angle. So for every z-axis, we have three angles to detect and to plot. So it's very long. With a automatic machine, electronic microscope is very, very easy. Okay, but just take in mind that it is very useful because you can detect the sense of shear, the vorticity, the kind of strain ellipsoid, and you can use, of course, quartz because it's easy, it is very common, but we use the calcite for the South Tibetan detachment because in central Nepal and western Nepal, the Grit sequence is made by calc silicate rocks in the upper part, and the Tethyan sequence is made by marbles in the lower part. So you have calc silicate and marble in contact. It's very difficult to put the boundary. And so we calculate temperature, by pitting condition, pressure, and also with a PhD by Laura Nania, that she is now working in Geological Survey of Canada. She made a very beautiful work with calcite because calcite is quite difficult as a mineral. It's not simple as a quartz, and there are not many people working on this. So she spent several months in Germany with Bernard Leys and Michael Stipe to understand the deformation. But at the end, she was able to publish three papers: structural geology, tectonophysics, and Geological Society of London. The tutor was Chiara Montomoli, and it was very nice work because she gained a lot of information by this kind of fabric. So keep in mind, if you have marbles, you can use also calcite. Okay, now I will show you an example by Xipolias. This is we are in Mediterranean area, Crete Island. This is Greece, Turkey is here, Africa is here, Italy is a little bit on the northwest. He used an app, this red one, with maybe low-grade metamorphic condition, very low metamorphic condition, to assess the strain approaching thrust. Through this PQ unit, it is a local name, but it is not important. So he took sample in a transect, of course, on the surface from one thrust to another. This one, this one, this one. It took several transactions, a lot of work for this. And the paper has been published in 2007 in Journal of Structural Geology. It's available. It is a very nice paper to see an application because he found a useful strain marker, such as this one. So he used all these kind of elongated quartz grain and the metaconglomerate to assess the amount of strain. So, for example, he compared also, uh, we are on the XZ section, by RFP method and by Frey method. If there is a difference in competence contrast, of course, there is a difference in the value by one method and by the other. If more or less a line along a line, it means that they give the same information, so there is not a big competence contrast. So it's just a good check for the method used. Used both the method. Okay. Use a different method, the Frey method, distance of the object, mean object ellipse using a elliptical object, mean radial length use elliptical object, a theta curve, clustered RFE method use elliptical object. So different mm, different method related to the changing in shape. But they so Frey and RFE is theta curve by Richard Lyle. That is a raffination of the RFE method. So more or less the same value. So all the methods are in keeping. They give good information. This is a good approach because by one single method you have some problem, but using this one different one, you can go much confident of the method. They used also the error bar error on the measurement. It's quite uncommon because usually one put the value, but it's difficult to assess. So more or less, he plotted the strain data with respect to the basal thrust. You have the strain ratio and the distance from the basal thrust. So there is a change in the strain ratio with different values. So approaching the basal thrust, of course, the strain increase up to very high value, maybe 10, 15, a very high value, that very uncommon. Use several different section. Okay, more or less, he checked the same with different approach, but more or less approaching the thrust, the strain increases a lot from axial ratio on the XZ section close to 3 or less to 3 up to 9, 10, 10, 9, 10. So very, very strong deformation. Okay, you also calculated some other different parameter, but I don't remember what is beta value, more or less. Okay, and at the end, he made also a comparison, a general comparison of the strain value in different situations all over the world. We are the Morklen up in the standard part of the Alps, Blue Ridge in USA, North Mountain Trust maybe also in USA, Himalayan Trust in eastern Nepal, and the Orleans Trust. I don't remember where is Orleans Trust. D. Cashman, maybe also North America. So you can see that more or less at the distance of few kilometers, and approaching the different thrust, the strain along the section increasing a lot. So more or less the same behavior. This, there is also the other part where strain decreases, going away. There are very few value. This is a paper by Goscombe 2006, but maybe after that some other values has been gained. So finite strain is also useful to characterize the amount of strain approaching the thrust, as one of you showed me yesterday, more or less. The most important thing is to have a good strain marker and to cut the rock along the principal plane of the strain ellipsoid. Okay, now I show you a little bit something about the software strain ellipse fit by Frederick Vollmer. This the reference, the web page, but you put ellipse fit on Google, you find quickly. It is a very nice software. There are several versions. Just a few months ago, 3.7, 3.8, 3.81, 82. We continuously improve the software. I prefer the older one because they are very simple. Because in the new one, it put a lot of statistics. Of course, it's very useful, but the manual is very complex to read. Anyway, uh, you can use some picture. This is a picture for a conglomerate that is present in the web page. You can use or the picture or the tracing paper with the boundary of the object. Automatically, it is very difficult to gain the shape of the object because you can use Photoshop, for example, or ImageJ, but you have to work a lot manually because the rock are strained, are very complex, and if you have a picture like this, it is not easy from the picture to select contrast, binary image, and to select correctly the boundaries. I usually make a lot of confusion, so you have to work a lot this. So one possibility is to use a tracing paper. So use a tracing paper. Manually, you draw the boundaries, and then you make a picture and work on. Otherwise, you work on directly on the picture, and you can you can gain the information about the boundary and the axial ratio in different way. These are the formed object. There is a function that you put the mouse here and the fill of a yellow the object and then calculate the volume, the area. But if the object is open or there are some pixel with the same color outside, maybe the yellow go boom all around the section. Otherwise, you can check the central point by the mouse and then he records the coordinate. Another possibility is maybe the best one is to find 5 points along the perimeter of the object, just five objects. He detect the elliptical shape, long axis, short axis, centroid, and orientation of the long axis. This is quite quick because just 5 objects maybe take care of to put the more distance point or the shorter distance another one. So you can see the elliptical shape. But anyway, he put the elliptical shape just when you made the last click on the fifth object. So in this way, you gain all the information in a very easy way. After that, he plot the information using a R-phi graph like this. So, and they calculate automatically the R axial ratio of the strain, and they put also on the Frey graph. Okay. Of course, there are other kind of information. Maybe instead of the Flink graph, use this kind of strange graph, but it is not useful. Or this that was used by Wellman, you calculating a strain by distorted angles in fossils. So there are possibilities, but I think Herfy and Fry are the most popular, most useful method. Just to example of the deformed object, we are in Sardinia, in the NAP zone, in the central part, in between the forest and the hinterland, and there are volcanic breccias deformed during the Carboniferous, and you can see that the cluster are strongly deformed and aligned in the same direction. So the strain is very high, and what we can say is that the strain is higher than the axial ratio, initial axial ratio of the object, because they are all aligned in the same direction. So when you put in a RFI graph like this, you can find all the point in this position. Mm. But these kind of cluster are very good strain marker. Here's another kind of breccia from the Permian of the Northern Apennines. The breccia reworked as a Paleozoic basement and was later involved in alpine orogenesis, contemporaneous more or less uh, the Alpi. Apennine orogenesis and alpine orogenesis. You can see different cluster, but different elongation because there are different cluster with different rheology, different composition. So in this kind of deformation, it is better to use Frey method because you use only the centroid position because this cluster are much more deformed. This one enriched in quartz are less deformed. So if you use the shape of the class, you make a mix. So the result is not good. But if you use the Frey method, is it's okay. You can gain a good information. Okay, now we can stop maybe 10 minutes and then we can download the software on your laptop and then we try Sorry. When you downloaded the program, you have also um, no? Okay. Okay, you have also some data and images in in a folder that is named example data. Do you have it? Okay, you can go to the shapes, diamictite, tracing, or diamictite JPEG. This is just the picture of the format diamictite. Ah, okay. Okay. And if you would like to digitize the shape to gain the information, oh, this is very small. You can use maybe this one. Okay, you click on this symbol, and you have a choice of a center point, ellipse axis, 5-point ellipse, quadrilateral shape, filled shape, line pair. Okay, we can try with filled shape that just you put the mouse on the object, you click, and nothing happens. Ah, okay. In this way, we found a good boundary with the object and depicted the strand ellipse with the long axis, short axis, and centroid. At the same time, he is recording the data in a file like this. Maybe oh, there are other objects in this way, in this form. Identification of the object, 1, 2, 3, 4, long axis, minor axis, the area, axial ratio, orientation, and so on. So you have all the data that you need to calculate strain. And you can go ahead. Yeah. Sorry? Ah, yes, yes. Also, yeah, you can use 5-point or center point, for example. Just you put here. Okay, there is also some this, but the best one, I think, is to use a 5-point ellipse. So you can choose your object like this, 1 point here, 1 point here. You can see the yellow dot, 3, 4, and 5. Okay. In this case, there is not a good approximation of the ellipse, so I try to do another time. So we can try with this one. 1, 2, 3, 4, 5. Here is a little bit better, but a little bit longer. Okay. In this case, the 5-point were put in a better way, because if you put, for example, the point very close, nothing happened. Nothing. Okay. Nothing. Okay. The Stan ellipse is very strange. So try to be accurate in this kind of picture. Another possibility is open image. Okay, you can use the trace. So in this way, maybe it is more easy. It's just the noise of the program. When there is an error, oh, in this way, it is very, very quick information. Yeah. Yes. Yes. Yeah. Maybe. But if you're okay. Mhm. Okay. Anyway, if you have a good picture, it is not so long to find the 5 points along the perimeter. So I suggest to use a picture just to be more quick. But up to you. It's not a problem. Okay. Okay. After that, when we have made a lot of this kind of measurement, maybe 40, 50 objects, you can try to plot, maybe fry plot. Okay. Oh, this is from another picture. Oh, because I uploaded before uh, another picture, but he plot all the centroid data, the position, and they made automatically the fry plot to calculate the finite strain. And the finite strain, okay, if you put the mouse on the fry plot, on the RF plot, he created this kind of plot with RF method, or maybe the clues plot. The clues plot is just a plot used at the beginning in the 40s, in the 50s by an American geologist working with deformed oolites, and they put just on the horizontal axis the minimal, the short axis of the object, and here the long axis. And usually, if there are no big problem of deformation, the object are nearly spherical, all the data should be aligned along this line. And in this way, you can calculate the strain. Of obviously, different angle of the line indicate different strain. R equal to 1, R equal to 10. So, but in this case, you can see that the objects are very far from one line. So this means that they are not perfectly spherical, but different elliptical shape. So it is not good. It is not good to use this kind of graph here. Maybe the RF graph is better. This kind of line, this R, axial ratio, the phi orientation, this kind of line are line of initial axial ratio of the object. So if you have point that fit several lines, you mean that in this case, you mean that you have different initial axial ratio of the ellipsoidal object in the deformed rock. But it is not a problem for this. I do not. Really nice. Visnando. It's strange.
Mm. This is history what I got from here. So I'm just not can be interpret that most saying, oh, well, the doctor we were the same way. The accelerations you can here the value of the air that we have more than the medium distribution of the acceleration. So this acceleration is the acceleration of the star. The shore on the shape that kind of set. Okay, you have to plan this one the testing with the that's the actual the value of the method is one. But anyway, you give the red one the position. Mhm.
in paper with black and white borders, and just to use the fill option. Just you click in this position, and they calculate the area, the perimeter, the long axis, short axis, orientation, the centroid position, and the data are put in a file like this that you can, well, much data that you can save somewhere, save as in some place, okay? And before saving or after saving the data, you can plot. You can use the fly plot, not so good. This in this file, or the RFI plot that is quite nice to. You have several point plotted, the line of initial axial ratio, and the red dot is just the position of the axial ratio of the strain ellipse and the orientation. Usually when I click here, appear the axial ratio below, but now not now, but just we checked. Sometimes the program has some problem in adapting to several objects. Anyway, if it is 1, 2, 3, 4, this close to, I don't know, for this 1, 2, maybe 1.7, and the orientation is maybe 28, 30 degrees, 29, 30, okay. Yeah. But usually when you click here, you have just below the position in the graph, so the axial ratio. I don't know why it doesn't work. Okay, we can close this plot. Another way is to calculate ellipse, to select some mean radial length eigenvector. This is made by calculation of 2D tensor, and the centroid. If you click OK in this page, oh, they give the result of the close plot. The close plot is where is close plot? Close plot is this one. It is not a so good graph because you have a lot of data here along this red line, but some data are along different lines. This means that the objects are not spherical, but with different ellipticity. So the data is not so good. But anyway, just a tentative. But in this file, oh, you have close plot results. You have the axial ratio is 1.4, because very different to 1.9 or 2 because of the confusion between elliptical object. In the other part of the file, you have mean ellipse calculation by maybe different kind of mean, arithmetic mean, or standard mean, or another different kind of mean. So you can read here the R is the axial ratio is 2.1.02, and C is orientation of the long axis. The 22 here 2 and 22, so more or less are the same value. This software gave a lot of statistic, but more or less with natural data, there's no big difference in between different methods. Okay, the harmonic mean, arithmetic mean, the harmonic mean, and the circular mean, a different kind of calculation with small differences. The arithmetic mean give a little bit higher value, 2.4. The harmonic mean is very good, 2.1. The harmonic mean is just dividing the number of objects, dividing the axial ratio elevated -1 plus axial ratio elevated -2. So a little bit different calculation that usually people found that is very close to the real strain of the object. So harmonic mean is a good approximation. And when, okay, so you can use
for strain in just this simple way. The best use is for the fry graph. Of course, I have no good large number of objects in my picture because I open again the image. Okay. But there is a reason why the fry plot is not so good because the fry plot is better used if the objects are of the same size. So this is a limitation, but you can check using this kind of plot because if it's the same object with the same size, when you plot, you put here the center, you define the other point around. So the high strain area with a lot of points is just is a good elliptical shape. But if you have a small object or bigger one, this small object, when you point your center here, go inside the void area. If you have a lot of these small objects, you have a confusion speed. This larger one has a distance very big, so go here. And when you have different sizes, you have confused strain ellipses, or in this case, not enough point, but there are too much different grain size and not good approximation of the strain ellipse. So it is important because can check the graph, the plot, so directly because you made the calculation, you plot, you say, okay, oh, in this case it is a bit better because I put away some graph, but anyway, you can see the general shape could be this one, but there are several points inside because of the smaller object present here. So anyway, you can use the RF graph. You can gain the information about acceleration and orientation. Also on the fly graph, you can use okay, the centroid are here. Okay. Okay, these are information. Anyway, you can calculate the strain ellipse by digitizing 5 point here and then calculate the strain of this picture. And you can compare the result from this strain and the strain obtained by the RF. If the results are similar or with small difference, it's okay. If the results are strongly different, means that there is a competent contrast in between the cluster and the matrix. And so you have maybe to avoid the RF calculation and use the fry graph calculation. And this is just the first step because you have this graph. This just a surface. So remember that you must use one principal plane, maybe Z or XZ. You are using this one. You need to use the other one. So with two planes, two principal planes, you are able to plot your sample in a clear graph. Maybe your sample for here, the flattening field. We can also calculate the distance from the origin of this point. So much more strain. Put the point far away from the origin, the origin point 1.1. So you can make some estimation of the formation different way. But you need at least two surfaces to have a 3D deformation and to correctly plot in the free graph. And if you are stuck the main center thrust, that the main center thrust here. Okay. You can collect the sample from here, 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 here. You calculate two section here, two section here, and then the 3D. In this program, you can gain the information about several things, but at the end you have R here, acceleration and orientation. And you can use also this data to plot, to calculate vorticity. Of course, in not the same rocks, because when you use rock cross-strain analysis, you have an object, an initial object that has been deformed and became elongated and underwent also some rotation. But the deformation and the rotation. For vorticity, you need to have the strain. For vorticity, you need to have a rigid object that rotate during deformation, during single shear or blue shear, but without internal deformation. They are strongly rigid and rotate continuously or not continuously, but the input data, you can get the input data also by this program. We can use the 5-point perimeter and we calculate the long axis, short axis, centroid, orientation, and the acceleration and the orientation are such that are data that we can use for vorticity. Do you remember the graph? Because for vorticity analysis, using porphyroblast, I use the orientation alpha, the acceleration here, 90 minus 90. Here, 1, 2, 3, 4, 5. Acceleration may be 1 and orientation 20, the point is 0, 2 and orientation 20, the point is 0, 2 and orientation maybe 45, the point is 0. So you have this kind of distribution, you detect the LC value, and you calculate the vorticity. But instead of gain manually the data, you can take a picture and upload with so the fit, ellipse fit, and digitize the boundary with 5 points. And so in the file you have acceleration and the orientation. You can select this column and try to put in Excel to put the value to perforate this graph. But I know it's just days. There will be time, but for this, okay, there is a graph. Okay, there is an Excel file. Okay. Excel is opening. Made by Xipolias or Fossen, where you can put your data. So this is the graph for vorticity. With the shape factor, V or the acceleration, not so much difference. And the angle between the long axis and the macroscopic foliation. And here you can put the short axis, long axis, ratio, or angle. Now there is no value. Don't know why. Okay, but anyway, in this column you can put your data, and automatically they are plotted on the graph. So just you collect the data from an Excel, put here. I don't remember if this program is set in the same way. Anyway, you put acceleration and angle, and you have the point here. So you can calculate also vorticity with the same data. But remember that for strain, the cluster should be deformed, so they rotate due to deformation. In vorticity, they should be rigid like this, so they rotate but not deform for vorticity. For strain, you have to deform the object. So different bases. You use the same acceleration orientation, but the basis is completely different. So you cannot apply vorticity and strain on the same object. Sometimes people do this, but it is not correct. Okay. Okay. So maybe some questions. Let's try to understand why this not work. So almost clear. So just so how to start to work with this software LipSvit. If you need, you can continue, and you can download also the manual of the program. It's very big, not easy, because there is a lot of statistics with respect to the initial version 1.1, 2.0, big statistic inside, but you can avoid most of the statistic if you use for fine strain. There is also a possibility to use displacement and kinematic calculation for GPS data, velocity data. So if you in the future we face this problem, you can use this fit. You can read the manual to understand how to manage this data, this kind of data. Okay. Some questions? Okay. Okay, thank you for your attention. Tomorrow, Mahesh Latur will tell you some about landslide and so on, and we will see you the day after tomorrow for the last day. We will speak about a lot about the Himalayas, okay. Exhumation models, the formation trust, high fellowship zone, much more interesting things. Okay, thank you very much. Yep.